1 light year, just 2 words. But when you try to grasp the distance, your brain melts. Get ready, these cosmic scales will blow your mind. Tonight, we're diving into something that sounds ordinary at first, yet turns out to be one of the most brain-stretching ideas in all of science: the light year. You've heard the term countless times. Astronomers use it casually when describing space, almost as if everyone already understands it. But most people don't realize this. The moment you truly understand what a light year represents, the universe stops feeling familiar. It's not just a large number. It's a distance so extreme that it pushes the limits of human imagination. And by the end of this journey, you'll see exactly why astronomers rely on this measurement and why no simpler unit could ever replace it. Before we continue, if you enjoy this kind of deep, thoughtful exploration, a quick like or subscription genuinely helps the channel grow. It takes a second for you, but it makes a real difference here. Now, let's begin. Let's start with something you already understand: distance. In everyday life, distance is intuitive. You know how far it is to the store, to your job, or to the next town. You've traveled these paths yourself, so they mean something. You understand them in terms of time, effort, and what you'll encounter along the way. A kilometer is roughly the distance you can walk in about 10 minutes at a relaxed pace. Measurements like this work perfectly for daily life. If someone tells you a store is 5 kilometers away, you instantly estimate the drive. You imagine traffic lights, familiar streets, maybe a landmark or two. The distance feels real. If a city is 200 kilometers away, you can plan for it. About 2 hours on the road. Fuel up the car, maybe pack a snack, plan a short stop. These distances fit neatly into human experience. We evolved to understand how far we can walk, how far we can see, and how far we need to travel to survive and navigate our world. But this intuition starts to break down as distances grow. New York to Los Angeles is about 4,500 kilometers. That's still a meaningful number. It's a 5-hour flight, something millions of people have done. You can picture the journey cities giving way to plains, then mountains, deserts, and finally the Pacific coast. Long, yes, but completely achievable. Even the size of Earth itself is something we can wrap our minds around. The planet's circumference is just over 40,000 kilometers. Early explorers proved it could be traveled, even if it took years. Magellan's expedition completed the first journey around the globe in the early 1500s, and today, commercial flights could circle the Earth in less than 2 days. Earth feels large when you're standing on it, but not unknowably large. In theory, it's a place you could fully explore. Now, let's go farther. The distance from Earth to the Moon is about 384,000 kilometers. This is where our familiar sense of distance starts to fail. There's no road, no scenery, no landmarks, just empty space. Pure separation. Reaching the Moon required some of the most powerful rockets ever built. Astronauts traveled at speeds of around 11 kilometers per second, nearly 40,000 kilometers per hour, about 400 times faster than highway driving. And even at that speed, the journey still took 3 days. 3 days of non-stop motion through nothingness, just to reach the closest object in space. And that's the Moon, close enough to see with the naked eye, close enough to study with binoculars, hanging quietly in the night sky. Yet it still demands days of extreme travel to reach. Once we move beyond the moon, kilometers begin to lose their usefulness entirely. The sun is about 150 million kilometers away. Try to imagine that distance. You can't not really. Your mind recognizes it as a large number, but it doesn't feel like anything. Human intuition simply wasn't built for distances on this scale. At the speeds used to reach the moon, a spacecraft would need more than 5 months to travel from Earth to the Sunday. Even the fastest spacecraft ever created, the Parker Solar Probe, reaches incredible speeds of nearly 200 kilometers per second by using the sun's gravity itself. And still, it takes months to complete its paths. What makes this even more striking is how familiar the sun feels. We see it every day. It warms our planet. It makes life possible. And yet, it's separated from us by a distance so vast that crossing it pushes our technology to its limits. And in cosmic terms, the sun is nearby. The next closest star, Proxima Centauri, is more than 260,000 times farther away than the distance from Earth to the Sunday. Suddenly, even 150 million kilometers feels small. This is why astronomers needed a new way to measure distance. Not to complicate things, not to sound impressive, but because kilometers simply stop working at cosmic scales. Measuring the distance to stars in kilometers would be like measuring countries in millimeters. Technically accurate, but completely useless. So astronomers introduced a different unit, the light year. And here's the key point to understand right away. A light year is not a measure of time. Despite the word year, it has nothing to do with how long something lasts. A light year is a unit of distance. It simply means how far light travels in 1 year. So why use light as the basis for a measurement? Because light is unique. It's the fastest thing that exists. Nothing in the universe can move faster, not because we haven't figured out how yet, but because it's impossible. This isn't a technological limitation. It's a fundamental rule of reality. The speed of light is constant. It never changes. No matter where you are on Earth, on Mars, inside another galaxy, or near the edge of the observable universe, light always travels at the same speed. That speed is about 300,000 kilometers per second. Let that sink in for a moment. Every second, light covers 300,000 kilometers. That number isn't a rough guess. It's been measured with extreme precision. The exact value is 299,792.458 kilometers per second. But for our purposes, 300,000 is close enough. That speed is almost impossible to imagine. In a single second, light could circle Earth more than 7 times. In the blink of an eye, it could wrap around the planet again and again. In 1 second, light could travel from New York to Los Angeles and back dozens of times. Nothing in everyday life moves anywhere near that fast. The fastest thing most people ever experience is an airplane. A commercial jet travels at roughly 900 kilometers per hour, about 1/4 of a kilometer per second. Light moves more than 1,000,000 times faster than that. Even the fastest car ever built barely reached 1/3 of a kilometer per second. Light is hundreds of thousands of times faster. And even our fastest spacecraft, the Parker Solar Probe, which can reach speeds of about 192 kilometers per second, is still crawling when compared to light. By cosmic standards, it's slow. When you flip a light switch in a room, the light reaches your eyes almost instantly. The distance is so small that the travel time, about 10 billionths of a second, is completely unnoticeable. As far as your brain is concerned, the light appears immediately, but it didn't appear instantly. It still had to travel. The time was just too short for you to detect. Now consider the Sunday. When you look up at the sun, you're not seeing it as it is right now. You're seeing it as it was about 8 minutes ago. That's how long light takes to travel from the sun to Earth, even at 300,000 kilometers per second. That has a strange implication. If something dramatic happened on the sun right now, if it dimmed, changed color, or even exploded, we wouldn't know about it for more than 8 minutes. The event would already have happened, but the information carried by light would still be on its way to us. The same idea applies closer to home. When you look at the moon, you're seeing it as it was about 1.3 seconds ago. That delay is small, but it's real. During the Apollo missions, astronauts experienced this delay constantly. Every word they spoke took over a second to reach Earth, and every response from mission control took another second to come back. Conversations had a noticeable pause, a quiet reminder that even light takes time to cross space. Light doesn't travel instantly. It has a speed, and even though that speed is enormous, it's still finite. This wasn't always obvious. For most of human history, people assumed light was instantaneous. You open your eyes, and the world appears. It feels immediate, so it seemed reasonable to think light had no travel time at all. That assumption changed in 1676, when a Danish astronomer named Ole Rømer studied the moons of Jupiter. He noticed something strange. The timing of the moons disappearing behind Jupiter changed depending on where Earth was in its orbit. When Earth was closer, the eclipses happened earlier. When Earth was farther away, they happened later. Rømer realized what was happening. Light wasn't arriving instantly. It was taking time to cross the changing distance between Earth and Jupiter. From this, he concluded that light had a finite speed. His estimate wasn't perfectly accurate. The size of Earth's orbit wasn't known precisely at the time, but the discovery itself was revolutionary. Light was fast, but not infinite. Today, we've measured the speed of light with extraordinary accuracy, using lasers, atomic clocks, and advanced instruments. We know it doesn't change with motion or location. And we now understand that this speed is deeply embedded in the structure of the universe itself. It's not just how fast light happens to move, it's a fundamental property of space-time. So a light year is simply the distance light travels in 1 year at this constant speed. If we calculate it, the number becomes staggering. Light moves at about 300,000 kilometers per second. There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365 days in a year. Multiply all of that together, and you get roughly 9.46 trillion kilometers. That's 1 light year. Not a unit of time, a unit of distance. The distance the fastest thing in the universe travels in a single year. And that's the number we're trying to wrap our minds around tonight. Because to truly understand space, to understand the distances between stars and our place in the cosmos, we first need to understand what a number like that actually means. And to do that, we need to talk about something even more basic. We need to talk about what a trillion really is. Most people don't have an intuitive sense of numbers this large. We hear words like million, billion, and trillion all the time in news headlines, government budgets, and net worths. And they all just blend together as big numbers. But the differences between them are enormous. A million is 1,000 thousands. If you saved $1 every single day, without ever missing a day, it would take you about 2,740 years to reach $1 million. That's a long time, but it's still something you can imagine. It takes you back to ancient civilizations, to early empires, to a time when humans were already building cities and recording history. A billion is 1,000 millions, and here the scale jumps dramatically. If you saved $1 every second, not every day, but every second, it would take about 32 years to reach a billion. If you started counting seconds the moment you were born and never stopped, you'd be in your early 30s by the time you reached that number. A million seconds is only about 11 and a half days. That feels manageable, but a billion seconds is 32 years. And a trillion? A trillion is 1,000 billions. If you counted to a trillion, saying one number every second without sleeping or stopping, it would take you over 31,000 years. And that's the scale we're dealing with when we talk about light years. Let me put that into perspective. 31,000 years is longer than the entire span of recorded human history. Agriculture, the foundation of civilization itself, only appeared around 10,000 years ago. Before that, every human on Earth lived as a hunter-gatherer, constantly moving, following animal herds, tracking seasonal plants, and adapting to a world that offered no permanence. Writing didn't exist. Cities didn't exist. Nations didn't exist. The first known writing systems emerged roughly 5,000 years ago in Mesopotamia. The Great Pyramids of Egypt were built around 4,600 years ago. The wheel, one of humanity's most important inventions, likely appeared about 5,500 years ago. To count to a trillion, you wouldn't just need to start early. You'd need to begin counting before all of that. You would have to start when humans still lived in small tribal groups, when there were no farms, no permanent homes, no written language, no organized societies. You'd be counting through the birth of agriculture, the rise of cities, the invention of writing, mathematics, and science. You'd count through every empire that rose and fell, every discovery, every war, every peace treaty, every triumph, and every catastrophe in human history. And even after all of that, you'd still be counting today. And you'd still have thousands of years left before reaching a trillion. Let's make this even more concrete. 31,000 years ago, modern humans were living during the last ice age. We used stone tools. We hunted woolly mammoths and giant ground sloths. Humanity had only recently begun spreading beyond Africa, slowly populating Europe and Asia. Language, as we understand it today, barely existed. Art was limited to the most primitive cave paintings. Technology consisted of sharpened rocks, wooden spears, and fire. That's how far back a trillion seconds takes you. Now remember this: 1 light year is 9.46 trillion kilometers. Every single one of those kilometers is real. It's not an abstract unit. A kilometer is the distance you can walk in about 10 to 12 minutes at a normal pace. A short walk, something you've done countless times without thinking about it. And a light year contains 9.46 trillion of those individual kilometers. 9.46 trillion separate, distinct, kilometer-long segments, each one roughly the length of a casual walk to a nearby store. So when we say a light year is 9.46 trillion kilometers, we're talking about a distance that completely dwarfs anything in everyday human experience. You can write the number down. You can calculate with it. You can plug it into equations. But truly understanding it, feeling what it means, is almost impossible. Our brains simply weren't built for numbers like this. We evolved to count the people in our group, the animals in a herd, the days until the seasons change. We're comfortable with dozens, maybe hundreds. With effort, we can handle thousands. But trillions are so far beyond our natural intuition that they might as well be infinity. So instead of jumping straight to a light year, the only way to make sense of it is to build up slowly, step by step, starting with distances we can almost understand, and watching how quickly they spiral beyond comprehension. Let's begin small. 1 light second. Light travels about 300,000 kilometers in a single second. That's roughly the distance from Earth to the Moon, and about 3/4 of the way back. Think about that. Light leaves Earth, reaches the Moon, which is 384,000 kilometers away, reflects back, and still hasn't even used up the full second. All of that happens in 1 second. During the Apollo missions, this distance had real consequences. When astronauts on the Moon spoke to Mission Control in Houston, there was a communication delay of about 1.3 seconds each way. The astronauts would speak, and Mission Control wouldn't hear it for over a second. When Houston replied, their response took another 1.3 seconds to reach the Moon. Every conversation had a built-in pause, nearly 3 seconds round trip. You can hear it clearly in the recordings. That brief silence isn't hesitation, it's physics. The unavoidable delay caused by distance and the fact that nothing, not even radio waves, can travel faster than light. Now scale that up. 1 light minute is 60 light seconds, about 18 million kilometers. The Sun is roughly 8 light minutes away from Earth, which corresponds to about 150 million kilometers. So 1 light minute is already about 12% of the Earth-Sun distance. If you could somehow stand on the surface of the Sun, which, of course, you can't, because it's a raging sphere of plasma with surface temperatures around 5,500 degrees Celsius, but if you could, and you look toward Earth, you'd be seeing our planet as it was over 8 minutes ago. If Earth suddenly disappeared, exploded, or changed in any dramatic way, you wouldn't know it immediately. The event would already have happened, but the light carrying that information would still be crossing space. You'd continue seeing Earth as if nothing had happened for more than 8 minutes. This delay isn't just a thought experiment. It has real, practical consequences. When NASA operates rovers on Mars, communication is never instant. At its closest, when Earth and Mars are aligned on the same side of the Sun, Mars is about 32 million kilometers away, roughly 2 light minutes. At its farthest, when the planets are on opposite sides of the Sun, the distance stretches to around 400 million kilometers, about 22 light minutes. That means every command sent to a rover like Perseverance takes between 2 and 22 minutes to arrive. And any data sent back takes just as long to return. You can't drive a rover on Mars the way you'd drive a remote-controlled car on Earth. The delay is far too long. Instead, engineers plan everything in advance. They analyze images from previous days, map out routes, write long sequences of commands, send them, and wait. If something goes wrong, if the rover slips, hits an obstacle, or gets stuck, there's no instant reaction. Engineers must wait for the information to arrive, analyze the situation, plan a solution, send new instructions, and then wait again. A problem that might take seconds to fix on Earth can take hours on Mars. Now scale up again. 1 light hour is 60 light minutes, just over 1 billion kilometers. That's a distance so large it's difficult even to imagine. At its closest approach, Saturn is about 1.2 light hours from Earth. Saturn, the ring giant visible to the naked eye, known since ancient times, is already more than 1 billion kilometers away. When the Cassini spacecraft orbited Saturn from 2004 to 2017, capturing stunning close-up images of the planet, its rings, and its moons, every signal it sent back to Earth took over an hour to arrive. Every command sent to the spacecraft took just as long to reach it. And this is still within our own solar system. There was more than an hour of delay between the moment Cassini took a photograph and the moment that image arrived on Earth. The spacecraft would capture a picture, convert it into digital data, and transmit that data as a radio signal traveling at the speed of light. Only after more than an hour would scientists on Earth finally receive it. By then, whatever Cassini had seen was already part of the past. Because of this delay, Cassini could never be controlled in real time. Engineers couldn't watch what the spacecraft was seeing and adjust its trajectory instantly, the way you might steer a car or fly a drone. There was no joystick, no live feed, no immediate response. Instead, mission teams had to plan far ahead. Entire sequences of commands were written days, sometimes weeks, in advance. These instructions were uploaded to the spacecraft all at once, and then engineers simply had to trust that Cassini would execute them exactly as intended. If something unexpected happened, Cassini was on its own. The spacecraft had to be intelligent enough to recognize problems, diagnose issues, and switch itself into a safe mode automatically. Because by the time a malfunction was detected, reported back to Earth, analyzed by engineers, and corrected with new commands, more than 2 hours would have passed. In that time, conditions could change completely. This is what space exploration looks like once distances stretch beyond human intuition. Now let's scale up again. 1 light day is 24 light hours, about 25.9 billion kilometers. At this scale, even our fastest spacecraft start to feel incredibly slow. Voyager 1, launched in 1977, is the most distant human-made object in existence. As of 2025, it's roughly 1 light day away from Earth. It has been traveling for nearly 50 years, moving at about 17 kilometers per second, or roughly 61,000 kilometers per hour. That speed is astonishing by human standards. At that velocity, you could cross the entire United States in just a couple of minutes. And yet, after nearly half a century of non-stop travel through the vacuum of space, with nothing slowing it down, Voyager 1 still hasn't reached a distance of even 1 full light day from Earth. That distance corresponds roughly to the heliopause, the boundary where the sun's influence finally ends and true interstellar space begins. This is where the solar wind, a constant stream of charged particles flowing outward from the sun, slows down and merges with the thin interstellar medium, the sparse gas that fills the space between stars. Voyager 1 crossed this boundary in 2012, becoming the first human-made object to enter interstellar space. It was a historic achievement, a milestone in exploration. And yet, in cosmic terms, Voyager is still right next door, still within a single light day of our Sunday. Now imagine a light week, 7 light days, about 181 billion kilometers. At this distance, nothing built by humans has ever traveled, and nothing likely will for many decades, perhaps centuries. This is deep space, far beyond the planets, far beyond the regions we've explored directly. Out here, the sun would no longer dominate the sky. It wouldn't flood everything with light and warmth as it does from Earth. Instead, it would appear as a very bright star. Brighter than most, certainly, but still, just a single point of light against a black background filled with stars. If you could somehow float at a distance of 1 light week from the sun, you'd see it as one star among thousands. For the first time, you'd truly feel that our sun is not special, just one star in a vast stellar population. Now stretch that distance further. 1 light month is roughly 30 light days, about 778 billion kilometers. From here, even with a powerful telescope, the sun would look like an ordinary star. The solar system, all its planets, moons, asteroids, and comets, would be compressed into a tiny region of space surrounding a single point of light. You might barely detect Jupiter as a faint dot. The inner planets would be lost entirely in the sun's glare. Everything we think of as our solar system, every world we've studied, every spacecraft we've sent, would feel small, distant, and insignificant. And now we finally reach 1 light year. 1 light year is 365 light days, 12 light months, 52 light weeks, 8,760 light hours, 525,600 light minutes, 31,536,000 light seconds. Notice how quickly the numbers explode. We began with a single light second, already an enormous distance by human standards. And step by step, we multiplied. 60 seconds, 60 minutes, 24 hours, 7 days, 30 days, 12 months. And only now do we arrive at 1 light year, 9.46 trillion kilometers. That's the distance light travels in 1 year, moving at 300,000 kilometers every single second, without stopping, for 365 days straight. This is why astronomers use light years, because stars are separated by distances measured in light years. Anything smaller simply stops making sense. Imagine trying to describe the distance to the nearest star using kilometers. Proxima Centauri is about 40 trillion kilometers away. That number is awkward, meaningless, and impossible to visualize. But say it's 4.24 light years away, and suddenly the distance becomes comparable. If one star is 4 light years away, and another is 40 light years away, you instantly understand the scale. One is 10 times farther than the other. Light years also connect distance with time in a powerful way. When you look at a star 4 light years away, you're seeing light that left that star 4 years ago. You are literally looking into the past. This connection is essential for understanding the universe. The speed of light isn't just fast. It's the ultimate speed limit. Nothing can exceed it. And this isn't a limitation we'll overcome with better engines or more advanced technology. It's a fundamental rule written into the structure of space-time itself. The speed of light is a cosmic constant. It defines how space, time, energy, and matter are connected. In 1905, Einstein's theory of special relativity revealed something extraordinary. As objects move faster and faster, approaching the speed of light, reality itself begins to behave differently. Time slows down for the moving object relative to a stationary observer. This isn't theoretical, it's been measured directly. Atomic clocks on fast-moving satellites tick more slowly than identical clocks on Earth. Mass, or more precisely, inertia, increases. The faster an object moves, the harder it becomes to accelerate it further. The energy required rises dramatically. As you approach the speed of light, the energy needed to go faster increases without limit. To actually reach the speed of light would require infinite energy, and infinite energy does not exist. This is why nothing with mass can ever reach light speed. To understand why this happens, think about everyday motion. If you're on a train moving at 50 kilometers per hour, and you throw a ball forward at 20 kilometers per hour relative to the train, someone standing on the ground sees the ball moving at 70 kilometers per hour. The speeds simply add together. But light doesn't behave that way. And that's where things start to get truly strange. It might seem obvious at first, and for everyday speeds, it works just fine. But Einstein turned that simple idea upside down when he showed that it breaks down as you approach the speed of light. Imagine you're on a spacecraft moving at half the speed of light, and you shine a flashlight straight ahead. You might think, okay, the light should just add up half the speed of light, plus the light from the flashlight. That's 1.5 times light speed, right? Wrong. The light doesn't care. It still moves at exactly 300,000 kilometers per second. From your perspective on the ship, the same. From someone standing still, watching you from far away, still the same. Every observer measures the same speed for light. No exceptions. It's mind-bending, almost impossible to intuitively grasp. So, how can this happen? The answer lies in the fabric of reality itself. Space and time adjust to keep the speed of light constant. If you're moving extremely fast, time actually ticks slower for you when compared to a stationary observer. Distances in the direction of your motion shrink, and these aren't tricks of the eye or errors in measurement. These are real physical effects. Time and space are not absolute. They are relative, depending on how you're moving. The one thing that is absolute, that stays the same no matter what, is the speed of light. This isn't just theory, it's been tested countless times. Particles in accelerators, speeding close to light's velocity, live longer than identical particles at rest. Time literally slows down for them. GPS satellites orbiting Earth give us another example. They move fast enough and are far enough from Earth's gravity that their clocks tick slightly differently than identical clocks on the surface. If engineers didn't account for this effect, your GPS would be off by several kilometers in just a few hours. The fact that GPS works so precisely is a direct proof that time dilation is real. And here's another example from nature: cosmic rays. These high-energy particles strike the upper atmosphere and create muons, tiny subatomic particles that decay in just a couple of microseconds. At that rate, even if they were moving close to light speed, they shouldn't make it to the ground before vanishing. Yet we detect them at Earth's surface all the time. Why? Because from our perspective, Their incredible speed stretches their lifetime. A muon's couple microsecond lifetime becomes long enough for it to reach the ground. Photons, the particles of light, are even stranger. They have zero rest mass, so they don't need infinite energy to reach light speed. In fact, they must always travel at light speed. They can't go slower or faster. From the moment they're created to the moment they're absorbed, they move at exactly 300,000 kilometers per second. That's just what they do. It's their nature. And this has huge implications for space travel. Even if we could build perfect propulsion systems, have unlimited energy, and solve every imaginable engineering problem, we still couldn't go faster than light. The 4.24 light-years to Proxima Centauri represents a hard minimum. Even if we could accelerate a spacecraft to nearly light speed, it would take at least 24 years to get there. And that's just the nearest star. Most destinations are vastly farther away. Science fiction comes up with creative ways to get around this, of course. Warp drives bend space around a spacecraft so it can effectively travel faster than light without technically breaking light speed. Wormholes are imagined as shortcuts through space-time, connecting distant points. Hyperspace is a fictional alternate dimension where faster-than-light travel might be possible. These are fascinating ideas and fun to think about. Some, like the Alcubierre drive, are based on theoretical physics. In 1994, Miguel Alcubierre proposed a way to contract space in front of a spacecraft and expand it behind it. But it comes with huge problems. It would require exotic matter with negative energy density, something we've never seen, and possibly more mass energy than exists in the observable universe. Even if that were solved, there are paradoxes. Faster-than-light travel could let you go backward in time, creating all sorts of logical contradictions. Wormholes, if they exist at all, are likely too unstable to travel through safely. Hyperspace? Pure fiction. No evidence supports its existence. So the speed of light isn't just a technical limit. It's a fundamental law of the universe, built into space-time itself. Nothing with mass can reach it. And that's why distances measured in light years aren't just convenient. They also highlight the absolute boundaries of what's physically reachable. To make it real, let's look at Proxima Centauri, our nearest neighbor beyond the Sunday. It's a red dwarf, tiny about 1/8 the Sun's mass and 1/17 its diameter. So faint you can't see it without a telescope. Red dwarfs like this make up about 70% of stars in the galaxy, but none are visible to the naked eye. Even though it's our closest stellar neighbor, you can't just point your eyes and see it. Proxima Centauri is 4.24 light-years away, about 40 trillion kilometers. Imagine this. The fastest spacecraft humans have ever built, the Parker Solar Probe, moving at 192 kilometers per second, would take roughly 6,800 years to reach it. Start your journey when humans first invented writing, and you'd still be traveling today, still thousands of years away. That's longer than all of recorded human history. All our empires, discoveries, and inventions could rise and fall while you're still en route. These ideas are fascinating, and some, like warp drives, even have a foundation in theoretical physics. Take the Alcubierre drive, proposed in 1994. It's a solution to Einstein's field equations that, in theory, could allow faster-than-light travel by compressing space in front of a spacecraft and expanding it behind. But there are huge obstacles. To make it work, you would need exotic matter with negative energy density, something we've never observed in reality. Some physicists even argue it might be impossible on fundamental grounds. Even if exotic matter exists, the amount required would be astronomical, possibly more mass energy than exists in the entire observable universe. Then there's the problem of causality. Faster-than-light travel could allow you to travel backward in time, creating paradoxes that defy logic. Wormholes, another theoretical shortcut, would likely be incredibly unstable. They might collapse before anything could pass through them. Keeping a wormhole open long enough to travel through could require more energy than exists in the entire universe. And again, any faster-than-light travel using a wormhole could allow time travel to the past, bringing the same paradoxes. Hyperspace? Pure speculation. It's a concept for science fiction stories, fun to imagine, but it has no basis in known physics or mathematics. There's no evidence that it exists or could exist. Based on more than a century of careful experiments and observations, the speed of light is an absolute barrier. It isn't something we can overcome with better engines, more fuel, or clever engineering. It's a fundamental law of nature. So when we talk about stars hundreds or thousands of light years away, we're talking about distances that may be completely unreachable, at least with any technology that obeys the laws of physics as we understand them. A light year isn't just a measurement of distance, it represents a cosmic boundary, a limit beyond which our everyday notions of cause and effect begin to fail. To make this more concrete, let's talk about Proxima Centauri, our nearest stellar neighbor beyond the Sunday understanding. It helps us grasp what it means when we say that even the closest stars are incredibly far away. Proxima Centauri is a small red dwarf in the Alpha Centauri system, which is actually a triple star system. Two of its stars, Alpha Centauri A and B, are Sun-like, orbiting each other every 79.9 years in a slow gravitational dance that's been going on for billions of years. If you could see them up close, you'd witness two suns circling one another against the backdrop of darkness in space. Proxima Centauri itself is tiny in comparison, about 1/8 the Sun's mass and only 1/17 its diameter. It's so small and dim that you can't see it with the naked eye. Despite being our closest stellar neighbor, you need a telescope to spot it. Red dwarfs like Proxima are actually the most common type of star in our galaxy, making up about 70% of all stars. Yet they're all so faint that none are visible without equipment. When you look at the night sky, the stars you see with your naked eye are either larger and brighter than the sun, or not stars at all, but planets. Now, the distance. Proxima Centauri is 4.24 light-years away, roughly 40,140 billion kilometers. That's a 40 followed by 12 zeros. To put that in perspective, the fastest spacecraft humans have ever built, the Parker Solar Probe, moving at 192 kilometers per second, would take about 6,800 years to reach it. Think about that. That's longer than all of recorded human history. Writing was invented only 5,000 years ago. You could have started your journey back then, moving non-stop at the fastest speed we can achieve. And even today, you'd still be on your way thousands of years from your destination. There have been proposals for faster spacecraft, and one of the most ambitious is the Breakthrough Starshot initiative, announced in 2016 by physicist Stephen Hawking and entrepreneur Yuri Milner. The idea is elegant and, in principle, scientifically sound. The plan is to use powerful ground-based lasers to accelerate tiny spacecraft to about 20% of the speed of light. The concept is almost unbelievably simple in its elegance. Imagine a spacecraft the size of a computer chip, weighing maybe a single gram. Attached to it is an ultra-thin light sail, reflective, and only a few atoms thick. Then, from Earth, massive arrays of lasers are focused on this sail. The laser light exerts pressure on the sail, and because the spacecraft is so incredibly light, it can be accelerated to tremendous speeds. At 20% of the speed of light, about 60,000 kilometers per second, such a probe could reach Proxima Centauri in roughly 20 years. Add another 4 years for the light speed signals to return to Earth, and we could, in theory, receive data from the star system 24 years after launch. That's within a human lifetime. You could launch a mission when you're young and potentially see the results before you die. But the challenges are enormous, and some might even be insurmountable with current or near-future technology. First, the lasers. The proposal calls for an array producing around 100 gigawatts, roughly the output of 100 nuclear power plants, all concentrated into a laser beam a few kilometers wide. That beam would need to track the tiny spacecraft perfectly as it accelerates. Any deviation and the sail drifts out of the beam, stopping the acceleration. The spacecraft would then coast at whatever speed it had reached, far below the target. Second, survival. At 20% of light speed, collisions with even the tiniest particle could be catastrophic. A single speck of dust, smaller than a grain of sand, striking the spacecraft at that speed would release energy equivalent to a large bomb. Shielding would be necessary, but every gram of shielding adds weight, and weight is the enemy when trying to accelerate a spacecraft with laser light. More weight requires exponentially more energy, and soon the task becomes almost impossible. Third, communication. A spacecraft this tiny would need a laser or radio transmitter powerful enough to send data back over 4.24 light-years. At such distances, signals spread out enormously. To ensure we receive anything intelligible, the transmitter must be extremely precise and efficient, all within a craft smaller than a postage stamp. Imagine trying to shout across an entire ocean and be heard clearly on the other side. Fourth, precision navigation. At 60,000 kilometers per second, the spacecraft crosses the orbit of Mars in just 40 minutes. The width of the solar system, from the Sun to Neptune, would be traversed in about 6 hours. There's no room for error, no slowing down, no mid-course corrections. Slowing down would require as much energy as speeding up, and our gram-scale spacecraft simply doesn't have it. It must fly past Proxima Centauri at exactly the right angle and distance to collect useful data. Once it passes, the spacecraft continues into the void, never to be seen again, drifting endlessly through interstellar space. So, while breakthrough Starshot is a brilliant concept grounded in real physics, it remains highly theoretical. The technology doesn't exist yet, and the challenges are formidable, perhaps impossible with anything we can currently build. Even if such a spacecraft were launched tomorrow, it would be at least 20 years before it reaches Proxima Centauri, and another 4 years for any data to return. That's a 24-year round trip for information, assuming everything works perfectly, something that, in the history of space exploration, has never been guaranteed. And this is just to reach our nearest stellar neighbor, the closest star beyond the Sunday. Even with technology that we can realistically build today, the rockets, materials, and computer systems we actually know how to engineer reaching Proxima Centauri would take not decades, but millennia. To make such a journey with humans aboard, we would need multi-generational spacecraft, massive vessels, capable of supporting crews for thousands of years. The people who finally arrived at Proxima Centauri wouldn't be the ones who left Earth. They would be the distant descendants of the original travelers, perhaps hundreds of generations removed, living their entire lives aboard a spacecraft, voyaging to a destination they had never seen, and that existed only in the stories passed down through countless generations. When you look up at the night sky, you are seeing stars at vast distances, and you are seeing them as they were, not as they are now. This is one of the most profound consequences of the light year. Distance and time are inseparable. You cannot separate where something is from when you are seeing it. Light travels at a finite speed. Incredibly fast, yes, but not instantaneous. When a star's light leaves it and travels through space toward Earth, it takes time to arrive. During that journey, things can change. The star might dim, brighten, shift color, or even explode. By the time the light reaches your eyes, the star you are seeing may be completely different, or it may not even exist anymore. Take Sirius, the brightest star in the night sky, for example. It is 8.6 light-years away. When you look at Sirius tonight, you are seeing light that left that star 8.6 years ago. You are literally seeing Sirius as it was when you were younger. If you are 20 years old, you are seeing Sirius as it appeared when you were around 11, probably in middle school. If you are 40, you are seeing Sirius as it was in your early 32nds. Sirius is a stable main sequence star, so it hasn't changed significantly in that time, but the principle remains. You are looking back in time every time you look at a star. Vega, another bright star, lies about 25 light-years away. If you are 25 years old tonight, the light you are seeing left Vega the year you were born. When that light began its journey, you did not exist. Your parents might have been seeing the light from Vega 25 years before that, 50 years ago in total. The Vega you see tonight is a younger version of the star, showing how it looked a quarter century ago, not as it is right now. Now consider Betelgeuse, the massive red supergiant in Orion, easily recognized as the bright reddish star marking Orion's shoulder. It is about 550 light-years away. The light reaching your eyes tonight left Betelgeuse in 1474, during the Italian Renaissance, before Columbus sailed to the Americas, when Leonardo da Vinci was 22 and Michelangelo was about to be born. The Byzantine Empire had fallen 21 years earlier, and the printing press had been invented just 2 decades prior. Most of Europe was still emerging from the Middle Ages. The modern world, as we know it, did not yet exist. And yet, the light from Betelgeuse has been traveling through space for over 5 centuries, crossing the vast darkness between that star and Earth to reach you tonight. Betelgeuse is especially interesting because it is a massive star nearing the end of its life. Unlike smaller stars, like the Sun, it burns fuel much faster. In astronomical terms, within the next 100,000 years or so, Betelgeuse will explode as a supernova. When that happens, it will briefly shine as bright as the full moon, visible even during the day. And yet, the light we see tonight shows Betelgeuse as it was centuries ago, a snapshot of history frozen in space, reminding us of the vast scales of both time and distance in the universe. It will be a spectacular event, one of the most dramatic astronomical sights visible from Earth in human history. But here's the twist: Betelgeuse might have already exploded. The supernova could have occurred centuries ago, maybe in 1600, 1700, or 1800. Yet we would have no way of knowing. The light from that explosion is still traveling through the void of space, moving at the speed of light, taking 550 years to reach us. So, if Betelgeuse exploded in the year 1700, we wouldn't see it until about 2250. The star could already be gone, destroyed in a violent, catastrophic supernova. And yet tonight, from our vantage point on Earth, it would still appear to shine calmly in the night sky, a ghostly echo of a past that no longer exists. Consider Polaris, the North Star, at about 445 light-years away. When its light began its journey toward Earth, the first permanent English colonies in North America hadn't yet been established. Jamestown would not be founded for another 12 years, and the Pilgrims wouldn't arrive at Plymouth Rock for another 26. William Shakespeare had started writing, but hadn't yet penned Hamlet, Macbeth, or King Lear. The United States wouldn't exist for another 180 years. And tonight, that ancient light enters your eye, connecting you across centuries and space to a time vastly different from today. Within about 20 light-years of Earth, there are roughly 130 known star systems. Some are single stars, like our Sun. Others are binaries, with two stars orbiting each other. Still, others are triple systems, like Alpha Centauri. Understanding this stellar neighborhood gives us perspective not just on the distances, but on the variety of stars in our cosmic backyard. Take Barnard's star, the second closest system to Earth after Alpha Centauri, about 6 light-years away. It's a red dwarf, smaller and dimmer than the Sunday. What makes it fascinating is its speed relative to us. It has the largest proper motion of any known star, moving across the sky faster than any other star as seen from Earth. Over decades and centuries, you can actually observe it shift position relative to other stars. In roughly 10,000 years, Barnard's star will pass closer to Earth than Proxima Centauri is now, becoming our new nearest stellar neighbor. Even then, it will remain nearly 4 light-years away. The distances between stars are so enormous that even stars moving toward each other take thousands or tens of thousands of years for their motion to make a noticeable difference. Wolf 359, about 7.9 light-years away, is one of the fastest-moving nearby stars, traveling at roughly 119 kilometers per second. That's quick by stellar standards. Most stars in our part of the galaxy move at just a few tens of kilometers per second relative to each other. Yet even at this speed, Wolf 359 is moving only about 0.04% the speed of light. Stars move, yes, but in the grand scheme of cosmic distances, they move painfully slowly. Even the fastest star nearby would take tens of thousands of years to cover a single light year. Sirius, 8.6 light-years away, is actually a binary system. Sirius A is a bright white main-sequence star, about twice the mass of the Sun, and it's the brightest star in our night sky, partly due to its proximity, partly because it's intrinsically luminous. Sirius B is completely different. A white dwarf, the dense remnant of a star that exhausted its nuclear fuel and collapsed. White dwarfs are fascinating. They are roughly the size of Earth, yet they carry the mass of a star. Sirius B, for example, packs the Sun's mass into a sphere the size of our planet. A teaspoon of material from Sirius B would weigh about 5 tons on Earth. Sirius A and B orbit each other every 50 years, locked together in a gravitational dance, each following an elliptical path around their common center of mass. Zooming out, the Milky Way itself is a spiral galaxy containing between 100 billion and 400 billion stars. And what we see in our night sky, the stars, the planets, the clusters, and nebulae, represents only a tiny fraction of what exists within our galaxy alone. When we look up, we're glimpsing not just points of light, but ancient history, immense distances, and the slow, majestic movement of countless stellar bodies across the cosmos. Counting the stars in our own galaxy is incredibly difficult. Imagine standing in the middle of a dense forest and trying to count every single tree in sight. Some are hidden behind others, some are barely visible. Now imagine, this forest is 100,000 light-years across, filled with hundreds of billions of stars, many dim, many obscured by clouds of cosmic dust. That's the challenge astronomers face when trying to tally the Milky Way's stars. Dust blocks our view in many directions, and the sheer size of the galaxy means we cannot see it all from any single vantage point. But using careful observations and statistical models, astronomers estimate there are somewhere between 100 billion and 400 billion stars, with the most likely number being around 200 to 300 billion. And our Sun? It is just one ordinary star among billions, a yellow dwarf of average size and brightness. From the galaxy's perspective, there is nothing remarkable about it. It's not the biggest, not the brightest, not the hottest, and not the coolest. It simply orbits in one of the spiral arms of the galaxy, about 26,000 light-years from the galactic center. That means the light we see from the center of the Milky Way tonight began its journey 26,000 years ago. At that time, humans were still hunter-gatherers, roaming the planet in small bands, following animal herds, gathering wild plants, and crafting tools from stone. Agriculture did not exist. Cities did not exist. Writing would not be invented for another 21,000 years. Everything we now think of as civilization, from the first farms and cities to empires and modern society, has unfolded while that light traveled across the galaxy, crossing unimaginable distances to reach us tonight. And when it finally does, it connects us with a time and place that are entirely alien, yet intimately tied to our cosmic perspective. The Milky Way stretches roughly 100,000 light-years across, from one edge of its spiral arms to the other. Even if we could travel at the speed of light, it would take 100,000 years to traverse it. To put that into perspective, modern humans, Homo sapiens, have existed for about 300,000 years. You could have begun a journey from Africa when the first modern humans appeared, traveled at light speed, and you'd only be 1/3 of the way across the galaxy today. Even at such incredible speeds, the distances involved are staggering beyond human comprehension. Our Sun orbits the galactic center at roughly 230 kilometers per second, which sounds astonishing. At that speed, one could theoretically circle the Earth in just under 3 minutes, or cross the United States in the same time. Yet even at this velocity, it takes the Sun 225 to 250 million years to complete a single orbit around the galaxy. The last time the Sun passed through its current galactic neighborhood, dinosaurs were just beginning to evolve. Since then, dinosaurs have lived, ruled the Earth for over 160 million years, gone extinct. Mammals have risen, and humans eventually appeared, and only now has the Sun returned roughly to the same spot it occupied when the first dinosaurs emerged. This cosmic rhythm, spanning hundreds of millions of years, gives perspective to both our Sun's journey and the relative brevity of human history. One of the most revolutionary discoveries in modern astronomy is the detection of exoplanets, planets orbiting stars beyond our Sunday. Until 1992, we knew only of one planetary system, our own. Astronomers long suspected that other stars might host planets, but there was no direct evidence. Then, in 1992, the first planets were discovered orbiting a pulsar, a highly magnetized, rapidly spinning neutron star. This was a shock to the astronomical community. Just a few years later, in 1995, the first exoplanet orbiting a Sun-like star was confirmed. Since then, the number of known exoplanets has exploded. As of 2024, astronomers have confirmed over 5,000 exoplanets, with thousands more candidates awaiting verification. One of the most fascinating systems discovered is TRAPPIST-1, located about 40 light-years away. This small red dwarf star hosts 7 Earth-sized planets, 3 of which are in the so-called habitable zone, where temperatures could allow liquid water to exist on the surface. Imagine looking at this distant star, knowing that planets not too different from our own might circle it, with conditions that could potentially support life. It brings a humbling perspective. The universe is not only vast, but it might also be teeming with worlds that, in some ways, mirror our own. But even TRAPPIST-1 is still our cosmic backyard. Beyond 40 light-years, the distances grow even more staggering. Barnard's star, the second closest star system after Alpha Centauri, is about 6 light-years away. It's a red dwarf, smaller and dimmer than the Sun, but fascinating because it has the largest proper motion of any known star. It moves across the sky faster than any other star as seen from Earth. Over decades and centuries, we can actually observe its motion. In roughly 10,000 years, Barnard's star will be closer to Earth than Proxima Centauri is now, becoming our new nearest stellar neighbor. Yet even at its closest, it will still be nearly 4 light-years away. Another nearby star, Wolf 359, lies about 7.9 light-years away and moves at about 119 kilometers per second relative to the Sunday. That's fast by stellar standards, yet still only 0.04% of the speed of light. Even stars moving rapidly relative to each other require tens of thousands of years to cover a single light-year. Then there's Sirius, 8.6 light-years away, the brightest star in our night sky. Sirius is actually a binary system, consisting of Sirius A, a bright white main sequence star about twice the mass of the Sun, and Sirius B, a white dwarf, the dense remnant of a star that exhausted its nuclear fuel. Sirius B is extraordinary. It has the mass of the Sun compressed into a sphere about the size of Earth. A teaspoon of its material would weigh roughly 5 tons on our planet. Sirius A and B orbit each other every 50 years, locked in a precise gravitational dance that has fascinated astronomers for centuries. Looking even farther, the Milky Way contains between 100 billion and 400 billion stars, though estimates vary because it is incredibly hard to count them all. Dust obscures our view in many directions. Dim stars are difficult to detect, and we are inside the galaxy itself, making a complete survey challenging, like trying to map a forest while standing among the trees. The most likely estimate falls between 200 and 300 billion stars. Our Sun is one of these countless stars, a humble yellow dwarf orbiting about 26,000 light-years from the galactic center. That means the light we see from the heart of the Milky Way tonight began traveling 26,000 years ago. When that light started its journey, humans were still hunter-gatherers, living in simple nomadic bands, using stone tools, and following animal herds. Agriculture hadn't been invented. Cities didn't exist. Writing wouldn't appear for another 21,000 years. Everything we think of as civilization, from the first farms to empires to the modern world, has happened while that light traveled across the galaxy. The Milky Way spans roughly 100,000 light-years, and even traveling at the speed of light, it would take 100,000 years to cross from one side to the other. Modern humans have existed for roughly 300,000 years, so if we had set out at the dawn of our species, we would only be 1/3 of the way across the galaxy today. Meanwhile, the Sun completes its orbit around the galactic center roughly every 225–250 million years. The last time it occupied its current location, dinosaurs were just evolving. Since then, they ruled for over 160 million years, when extinct, mammals rose, and eventually, humans appeared. Only now has the Sun returned to the same approximate position it held when the first dinosaurs appeared. The discovery of exoplanets has revolutionized our understanding of the galaxy. Until 1992, we only knew of our own solar system. Then, the first planets around a pulsar were found, followed in 1995 by a planet around a sun-like star. Today, more than 5,000 exoplanets have been confirmed, with thousands more candidates awaiting verification. Systems like TRAPPIST-1, Barnard's Star, Wolf 359, and Sirius revealed the rich diversity of our cosmic neighborhood and the vast distances that separate even the nearest stars. The universe, it seems, is both unimaginably vast and astonishingly full of worlds. Every point of light in the night sky represents a story, a history, a journey across time and space that stretches far beyond human comprehension. When we look up at the stars, we are not only seeing distant suns, but also glimpsing the past, seeing light that left those stars decades, centuries, or even millennia ago. Each photon carries a message, a piece of cosmic history traveling across unimaginable distances, connecting us to the universe in ways both profound and humbling. The discovery of the TRAPPIST-1 system in 2017 was nothing short of revolutionary. For the first time, astronomers had confirmed that a small red dwarf star, one of the most common stars in our galaxy, could host multiple rocky planets. Red dwarfs make up about 70% of all stars in the Milky Way, so the implications of this discovery are staggering. Rocky planets, planets with solid surfaces like Earth, could be incredibly abundant throughout the universe. The TRAPPIST-1 system contains 7 such planets, tightly packed around their star, orbiting much closer than Mercury orbits our Sunday. Yet, because TRAPPIST-1 is small and cool, 3 of these planets lie within its habitable zone, receiving roughly the same energy from their star as Earth does from the Sunday. Imagine standing on one of these planets. The sky would be crowded with neighboring planets, looming large, some appearing bigger than the Moon looks from Earth. The planets are so close together that traveling from one to another would be far easier than moving between planets in our own solar system. These worlds orbit in a delicate gravitational ballet, their motion precise and predictable, yet far faster than anything we can achieve with our current technology. When we observe TRAPPIST-1 today, we are seeing it as it was 40 years ago, in 1985. Light carries information across vast distances at 300,000 kilometers per second. But even this seemingly impossibly fast speed is finite. Every photon reaching our eyes is a message from the past. If intelligent life existed on one of these planets, developed radio technology, and began broadcasting signals toward Earth in 1985, those signals would only just be arriving now. If we detected a message and sent a reply, it would take another 40 years to reach them. That's an 80-year round trip for a single exchange of information. You could ask a question and die of old age before ever hearing the answer. This sobering reality highlights one of the greatest challenges of interstellar communication. Even the fastest signals in the universe are bound by the speed of light. Even within our own solar system, these delays are tangible. Consider Voyager 1, the most distant human-made object. It is currently about 24 light hours away. A command from Earth takes a full day to reach it, and any data it sends back takes another day to return. That means a two-way conversation with Voyager requires 48 hours, 2 days, in which anything can happen on the spacecraft without human intervention. It must operate autonomously, solving problems by itself, relying on pre-programmed instructions for events that Earth-based engineers cannot yet react to. Similarly, the New Horizons mission that flew past Pluto in 2015 highlights the difficulty of distance in space exploration. At its closest approach, New Horizons was roughly 4.5 light hours away. All data it collected during its brief encounter, images, measurements, and readings, had to be stored on board, transmitted slowly back to Earth over months, and interpreted long after the flyby occurred. Every photon sent back carried a story from the past, a record of a moment millions of kilometers away, arriving years later. TRAPPIST-1 and these missions underscore a profound truth. Distance and time are inseparable in space. Every light year, every photon, every signal is a snapshot of the past. The universe is not just vast in space, it is vast in time. Even if we could one day travel at near light speed, the light we see from distant stars would always be history, not the present. To understand the scale, consider Sirius, the brightest star in our night sky, located 8.6 light-years away. When you look at Sirius tonight, you are seeing it as it was 8.6 years ago. If you are 20 years old, the Sirius in the sky tonight is the same as it was when you were about 11. And yet, to us, that delay is almost imperceptible because the timescales of human life are short compared to the speed of light. For more distant stars, this becomes astonishing. Betelgeuse, the red supergiant in Orion's shoulder, lies about 550 light-years away. The light reaching Earth tonight began its journey during the Italian Renaissance, before Columbus sailed to the Americas. When Leonardo da Vinci was just a young man, Michelangelo had not yet been born, and Europe was still emerging from the Middle Ages. The photons entering your eyes now carry a story of 550 years ago, a ghostly image of a star that may have already exploded in a supernova centuries ago, a spectacular event still invisible to us. Even our galactic neighborhood is immense. Within about 20 light-years of Earth, there are around 130 known star systems. Some are single stars like the Sun, others are binary or even triple systems like Alpha Centauri. Barnard's star, about 6 light-years away, is moving toward us relatively quickly, with the largest proper motion of any known star. Over thousands of years, it will become our closest stellar neighbor. Yet even at its high speed, it will remain nearly 4 light-years away, a distance so vast that human intuition struggles to comprehend it. Wolf 359, another nearby star, at 9 light-years, moves at 119 kilometers per second relative to the Sunday. That is fast by stellar standards, yet still only 0.04% of the speed of light. The scale of the Milky Way galaxy itself is staggering. Estimates suggest between 100 billion and 400 billion stars. With our Sun being an ordinary yellow dwarf, neither particularly big nor bright, sitting in one of the galaxy's spiral arms, about 26,000 light-years from the galactic center. The light we see from the center tonight left 26,000 years ago, long before human civilization as we know it existed. Humans were still hunter-gatherers, using stone tools and following herds across the savannah. Agriculture, cities, writing, all of it would happen during the journey of that light. To cross the Milky Way at light speed would take 100,000 years. If humans had set off on such a journey when the first Homo sapiens appeared 300,000 years ago, they would still be only 1/3 of the way across the galaxy today. Perhaps the most exciting development in modern astronomy has been the discovery of exoplanets, planets orbiting stars beyond our Sunday. Until 1992, we knew of only our solar system. Then, astronomers discovered planets orbiting a pulsar. By 1995, the first planets orbiting a sun-like star were detected. Today, we know of over 5,000 confirmed exoplanets, with thousands more candidates. Some, like the TRAPPIST-1 planets, are Earth-sized and lie in the habitable zone. Others orbit exotic stars in conditions wildly different from our solar system, yet they remind us that planets are common, perhaps ubiquitous, in our galaxy. The TRAPPIST-1 discovery reveals just how densely packed and dynamic planetary systems can be. The planets orbit closer together than Mercury, and Venus orbit the Sun, yet the gravitational choreography is precise, stable, and awe-inspiring. Standing on one of these planets, seeing neighboring worlds rise and set in the sky would be a spectacle unlike anything on Earth. Communication across these distances, however, remains daunting. Even with radio waves traveling at light speed, sending a message to TRAPPIST-1 and receiving a reply is an 80-year process. To send a probe with current technology is even more challenging. Breakthrough Starshot, an initiative proposed by Stephen Hawking and Yuri Milner in 2016, imagines using ground-based lasers to accelerate a tiny probe to 20% of light speed, reaching TRAPPIST-1 in just 20 years. Yet the engineering challenges are immense. Focusing a massive laser array across astronomical distances, surviving collisions with space dust at incredible speeds, and transmitting data back over 4.24 light-years. The probe would pass the star system at breakneck speed, with only a few hours to gather images before moving into the void of interstellar space forever. Even when humanity begins to imagine reaching these worlds, the universe reminds us of its staggering scale, its patience, and the finite speed of light. Every star we see, every photon reaching us, is a glimpse into the past, a story that began long before we existed. The TRAPPIST-1 system, with its 7 rocky planets orbiting a dim red dwarf, is a vivid reminder of the possibilities awaiting discovery, yet also a humbling testament to the challenges of traversing and communicating across the cosmos. Every command sequence for a spacecraft had to be programmed weeks or months in advance. There was no room for improvisation, no ability to react in real time to what the spacecraft was seeing or experiencing. Mission controllers had to anticipate every scenario, every anomaly, every solar flare, every potential collision with micrometeoroids. Every calculation, every maneuver, every adjustment had to be carefully thought out, with trust that the spacecraft's onboard systems could execute commands flawlessly while thousands, even millions of kilometers away. A single mistake could mean the loss of the entire mission. Now, imagine extending that challenge to human colonies on another star, such as a planet orbiting Proxima Centauri, our nearest stellar neighbor, 4.24 light-years away. You want to send a simple message. How are the crops? Is everyone healthy? Are there problems we should address? That message doesn't arrive instantly. It travels at the speed of light, 300,000 kilometers per second. Yet it still takes 4.24 years to reach the colony. That's 4 years, 2 months, and about 20 days before the first word is received. If the settlers respond immediately, carefully composing their message and sending it back at the speed of light, it takes another 4.24 years for the reply to return to Earth. That's over 8 years for a single exchange of information. By the time you hear back, the crops you asked about were harvested years ago. The sick person you inquired about may have already recovered or tragically passed away. Advice, guidance, or emergency instructions sent from Earth would arrive years out of date, often useless in the moment. This is not just inconvenient, it changes everything about governance, society, and communication. Real-time conversations, quick decisions, debates, negotiations are completely impossible. A diplomatic negotiation with a colony around Proxima Centauri could span decades, with each side writing detailed, carefully considered responses, knowing it would take years before the other party read them and another few years for their reply to return. Political decisions on Earth could change completely in the time it takes a message to arrive. New governments, new policies, and new emergencies could render directives obsolete before they even reach their destination. In this scenario, a colony could not be governed remotely from Earth. The settlers would need full autonomy, empowered to make decisions on resource allocation, emergency responses, conflict resolution, and societal management. They would have to become self-reliant, capable of thinking and acting independently in ways that Earth-based authorities could not. Waiting years for approval or instructions for every decision would be unfeasible, even dangerous. Over time, Earth and the colony would drift apart culturally and socially. They'd share a common origin and history up to the moment of departure. But after that, they would diverge. Customs, laws, languages, and even social norms might evolve in different directions. The colony would solve problems using its own logic, shaped by its unique environment, technology, and circumstances, while Earth continued along a separate path. Centuries later, Earth and its colony might barely recognize each other as part of the same civilization. They would be connected by letters from the past, messages frozen in time, yet unable to maintain the continuous, immediate connection that binds societies together. The situation grows even more extreme for colonies farther away. A settlement 10 light-years away would experience a 20-year round-trip communication delay. Imagine sending a letter to your children living there. By the time it arrives, they might be adults with families of their own. Their reply could return decades later, possibly after your death. Decisions, advice, even love and familial guidance would always arrive late, filtered through the relentless passage of time. The farther humanity reaches into the stars, the more each colony becomes an independent civilization, evolving in isolation while remaining tethered to Earth only through messages from the past. This is the sobering reality of space travel on an interstellar scale. Distances measured in light years aren't just astronomical, they are temporal. Every journey, every message, every attempt at contact is constrained not just by space, but by the finite speed of light. When thinking about humanity spreading into the stars, we must confront the fact that even with perfect technology, communication and governance will be bound by the universe itself. Colonies will become self-sufficient worlds, time-separated cultures, living with Earth's guidance, not as contemporaries, but as ancestors. Interstellar travel and settlement will not just challenge our engineering or propulsion, it will challenge our concepts of society, family, governance, and human connection. We may leave our homeworld, but in doing so, we leave behind the immediacy of human contact. Letters, data streams, messages, they all carry the echo of a past era, shaping the future in ways both profound and unpredictable. In the vastness of space, distance is time, and time is the ultimate boundary that separates civilizations, even those that share a common origin. If you tried to communicate with a distant civilization even a few dozen light-years away, the experience would be utterly alien. You wouldn't just be dealing with distance, you'd be dealing with time itself. You'd exchange letters or, more realistically, messages across decades, like correspondences from entirely different eras. You could share news, advice, or discoveries, and in some abstract sense, remain in touch. But the ordinary rhythms of conversation, the give and take of human relationships, would vanish. You couldn't talk, argue, laugh together, or solve problems in real time. A civilization 100 light-years away would create a truly staggering communication gap, a 200-year round-trip delay. If you sent a message today, you, your children, your grandchildren, even your great-grandchildren would all likely be dead before a reply returned. Perhaps only your great-great-great-grandchildren, living in a world almost unimaginable to you, might finally read an answer. This means conversations would literally span generations, with people sending messages to complete strangers, descendants of people they would never meet, receiving messages from people long dead. Civilization itself would fragment across time, connected only by delayed transmissions, like a chain of echoes stretching across the centuries. Yet there is another way to traverse this gap, one that doesn't depend on waiting for decades or centuries for messages to arrive. This is Einstein's time dilation, a strange and almost science-fictional effect, but one confirmed by countless experiments. This isn't speculation. It's as solidly established as gravity or electromagnetism. As you approach the speed of light, time itself slows down for you relative to people at rest. This isn't a quirk of clocks or measurement. Your heartbeat, your thoughts, your metabolism, your very aging all slow down from the perspective of stationary observers. Yet, from your perspective, sitting in your spacecraft, everything feels perfectly normal. Seconds, minutes, years all flow as usual. It's everyone else's time that races forward while yours stretches out. Imagine boarding a spacecraft capable of reaching 99.9% of the speed of light. Not quite light speed, but close enough for dramatic effects. You set off toward a star 10 light-years away and then plan to return to Earth. From the viewpoint of observers on Earth, the round-trip journey takes roughly 20 years, 10 years each way at nearly light speed. They would watch your spacecraft streak across the stars, taking 2 decades to complete its path. But for you aboard the ship, the story is entirely different. Time dilation means time is moving far slower for you. At 99.9% of light speed, time passes about 22 times slower than on Earth. While 2 decades fly by on your home planet, you experience only about 11 months of life. You step off the spacecraft having aged less than a year, while everyone you know has aged 20 years. Your younger sibling might now be older than you. Children you haven't yet had might now be adults. You have, in effect, traveled into the future of your world. If you push the speed even further to 99.99% of light speed, you could visit a star 100 light-years away and return. A journey that from Earth's perspective takes over 200 years. Yet from your perspective aboard the spacecraft, thanks to extreme time dilation, the entire journey might take only a few years. You live through a handful of Earth years, aging modestly, while entire human generations pass by back home. You emerge from the stars almost as if stepping out of a time machine, witnessing a world transformed, familiar, yet profoundly changed. This is the strange reality of near light speed travel. Distances measured in light years are not just spatial barriers, they are temporal barriers. To move across them is to move not only through space, but through time itself. A voyage at these incredible speeds allows a traveler to slip into the future, seeing the consequences of centuries of human history unfold, while their own life experiences only a fraction of it. It's a kind of interstellar time travel that obeys the laws of physics rather than the imagination. The profound implication is that even if humanity achieves the technology to travel near light speed, the universe will remain staggeringly vast, and Earth and distant colonies will continue to experience time at radically different rates. Space isn't just an empty void to cross. It's a dimension intertwined with time, stretching journeys into lifetimes and lifetimes into centuries. Those who traverse it at near light speeds will return as both pioneers and temporal voyagers, observers of a future they never truly lived on Earth, forever separated from the timeline of those they left behind. But when you finally return to Earth after traveling at near light speed, those 200+ years haven't passed for you, they've passed for everyone else. Everyone you once knew would be long gone. Your parents, siblings, friends, all vanished into history. The world itself would be almost unrecognizable. Political systems would have risen and fallen. Technologies would have leaped forward in ways you could hardly imagine. New languages might have emerged. Old ones evolved or disappeared. You'd step off your spacecraft into a future so alien it would feel like another planet. You would literally be a traveler from the past, encountering a society whose culture, values, and even landscapes might have transformed entirely during the time you experienced as mere months or years. Now, let's zoom out even further. The observable universe stretches far beyond the boundaries of our solar system, beyond even our galaxy. It is defined by the region of space from which light has had time to reach us since the Big Bang. The universe itself is roughly 13.8 billion years old, and for all that time, light has been traveling toward us. But because the universe has been expanding as the light travels, the observable universe is far larger than 13.8 billion light-years across. In fact, it has a radius of about 46.5 billion light-years, giving a total diameter of roughly 93 billion light-years. This represents the edge of what we can possibly see, the cosmic horizon. Beyond that horizon, regions of space are moving away so quickly that their light will never reach us, no matter how long we wait. It's not a limitation of our technology. Our telescopes aren't weak. The light simply hasn't had time to reach us, and in some cases, it never will. Within this unimaginably vast observable universe, there are roughly 2 trillion galaxies, each containing billions or even trillions of stars. Multiply it all together, and the total number of stars in the observable universe is estimated at around 200 billion trillion, a 2 followed by 23 zeros. Almost every star is likely orbited by at least one planet, meaning the universe is literally filled with worlds, planets beyond counting, many perhaps even capable of hosting life. There are more worlds than we could ever hope to visit, even if we had unlimited time, energy, and technology. And yet, these worlds are not scattered randomly. At the largest scales, the universe has a remarkable cosmic structure. Galaxies form clusters, held together by gravity. These clusters group into superclusters, gigantic structures containing hundreds or thousands of galaxies, and these superclusters themselves stretch out in enormous filaments, like threads in a vast cosmic web, spanning hundreds of millions of light-years. Between these filaments are voids, enormous regions with almost no galaxies at all, sometimes hundreds of millions of light-years across, creating an intricate pattern of structure and emptiness on the grandest scales. The universe is expanding, and this expansion isn't just galaxies moving through space. Space itself is stretching, carrying galaxies along, like raisins rising in a loaf of bread. Nearby objects, like the Earth and Moon, are unaffected. The gravitational bonds between them overpower the expansion. Our solar system isn't stretching. The planets stay locked in their orbits. Gravity keeps our galaxy intact too, holding the stars together against the pull of expansion. But on cosmic scales, between distant galaxies and clusters separated by millions or billions of light-years, the expansion dominates. Galaxies appear to recede from us, and the farther away they are, the faster they seem to be moving. This is not because they are speeding through space under their own power, it is space itself expanding beneath them. Every day, the universe grows a little larger, stretching the distances between galaxies, expanding the stage on which all cosmic history plays out. It is a reminder that while we might feel our world as vast and infinite, it is only a tiny part of a universe that is truly beyond comprehension, stretching out over tens of billions of light-years in every direction, filled with countless suns, planets, and possibilities. Even though those distant galaxies are essentially sitting still in their own local regions of space, the space between us and them is stretching, and over immense distances, that stretching becomes overwhelming. For galaxies far enough away, the expansion is so extreme that the distance between us and them grows faster than light could ever travel. And this doesn't violate Einstein's cosmic speed limit. The galaxies themselves aren't moving faster than light. They are essentially stationary in their own local space. It's space itself that is expanding, carrying the galaxies with it, stretching the cosmic fabric like a rising loaf of bread. Imagine trying to walk on a treadmill, moving backward faster than you can walk forward. No matter how fast you move, you are still being carried backward. That's exactly what happens with these galaxies. Even if light were emitted toward us from those regions, it will never arrive, not in a billion years, not in a trillion, not ever. There's a cosmic horizon, a boundary beyond which the universe is forever invisible to us. This isn't about patience or telescopes. This is a fundamental limitation of the universe itself, written into the structure of space-time. And yet, despite this enormous emptiness and isolation, when we consider the sheer number of stars and planets, the 13.8 billion year history of the universe, and the fact that life arose relatively quickly on Earth once conditions were right, it seems almost inevitable that life should exist elsewhere. Perhaps intelligent life capable of technology exists somewhere out there, sending signals across the void, exploring its own corner of the galaxy. But here's the paradox. We haven't detected a single sign of such civilizations. No alien radio signals, no blinking lasers across interstellar space, no megastructures, no evidence of gigantic engineering projects. The universe seems unnervingly silent. This puzzle is famously called the Fermi paradox, named after physicist Enrico Fermi, who casually asked the profound question, Where is everybody? Part of the answer may lie in distances measured in light years. The gaps between stars are unimaginably vast, creating almost insurmountable barriers for communication and travel. Our own radio signals, TV broadcasts, and radar emissions have been leaking into space for about 100 years. They expand outward in a growing sphere, traveling at the speed of light, 300,000 kilometers per second. That might sound immense, but consider that the Milky Way galaxy is about 100,000 light-years across. Our broadcasts have barely reached a tiny fraction of the galaxy. Even in that 100 light-year sphere, the signals are fading, spreading thinner and thinner as the sphere grows. By the time they reach a star tens of light-years away, the signals are so faint that they would be almost impossible to detect above the background noise of space. Any civilization trying to notice us would need enormously powerful instruments, pointed in exactly the right direction, tuned to the exact frequency, and scanning at the exact time. One small deviation, and our signals are lost in cosmic silence. This helps us understand why the Fermi paradox is so compelling. It isn't that alien civilizations don't exist. It could be that the universe is too vast, distances too enormous, and communication too slow for us to hear or see each other. The silence may be a result of cosmic isolation rather than absence. Now, consider what this means for us as a species. If we ever hope to send humans beyond our solar system to even the nearest star, Proxima Centauri, 4.24 light-years away, the challenges are immense. At the speed of light, a message takes 4.24 years to reach them. If they respond immediately, that reply takes another 4.24 years to get back. That's over 8 years for a single exchange of information. Ask about the harvest, the health of their children, or a sudden crisis, and your answer comes years too late. Governance, diplomacy, and society cannot operate in real time across such distances. A colony even 4 light-years away would need to be fully autonomous, making all its decisions independently, from resource management to conflict resolution, because Earth-based guidance would always arrive outdated. Expand this to a colony 10 light-years away, and the round-trip communication takes 20 years. Your messages to your children would arrive after they've become adults. Their replies might come back when your grandchildren are grown. Imagine trying to run a government, a business, or even a family across such distances. Everything moves on a multi-decade timescale. Now imagine a civilization 100 light-years away. Any conversation spans centuries. You might send a message, but neither you, your children, your grandchildren, nor even your great-grandchildren will live to hear a reply. Only your distant descendants, living in a world you can barely imagine, could respond. Communication becomes a form of time travel, exchanging words across generations, connecting people separated not just by space but by time itself. But there's an even stranger twist when you consider space travel near light speed. According to Einstein's theory of relativity, as you approach the speed of light, time slows down for you relative to stationary observers. This isn't theory, it's been confirmed countless times, from particle accelerators to GPS satellites. It isn't just clocks ticking slowly. Your heartbeat, thoughts, aging, metabolism, everything moves more slowly from the perspective of someone watching you from afar. Yet inside your spacecraft, time feels normal. Imagine boarding a spacecraft capable of 99.9% the speed of light. You set course for a star 10 light-years away. From Earth, that journey takes a little over 20 years. But thanks to time dilation, you personally age only 11 months. You return to Earth having lived less than a year, while everyone you know has aged 2 decades. Your younger sibling might now be older than you. Your children could be adults, perhaps older than you. You have literally traveled into the future of your friends and family. If you could go even faster, at 99.99% light speed, and travel to a star 100 light-years away and back, over 200 years could pass on Earth. From your perspective, the journey might take only a few years. You'd experience a short lifetime of travel, yet return to a world unrecognizable, where centuries of human history have unfolded while you were gone. Political systems would have changed, technologies advanced, cultures evolved, languages transformed. You'd be a visitor from the past in your own future. Now, zooming out even further, consider the observable universe. Light has been traveling toward us since the Big Bang 13.8 billion years ago. Yet the observable universe is much larger than 13.8 billion light-years because space has been expanding during that time. Its radius is about 46.5 billion light-years, meaning the diameter is roughly 93 billion light-years. This is the limit of what we can see beyond it. Space is receding so fast that light will never reach us. Within this observable universe are an estimated 2 trillion galaxies, each containing billions or trillions of stars. The total number of stars is roughly 200 billion trillion, a 2 followed by 23 zeros. Most stars likely have planets, meaning there are probably more worlds than we could ever count or visit, even with unlimited time and technology. At the largest scales, the universe is structured, not random. Galaxies form clusters, clusters form superclusters, and superclusters connect in filaments stretching hundreds of millions of light-years, with vast voids in between. Space itself is expanding, stretching the cosmic web, carrying galaxies away from one another, like raisins rising in bread dough. For nearby objects, gravity dominates, keeping planets in orbit and stars bound within galaxies. But over hundreds of millions of light-years, the expansion becomes dominant. Some galaxies are receding from us at speeds faster than light, not because they're moving through space, but because space itself is stretching between us. There are regions of the universe that are forever unreachable, eternally isolated from us. The universe is vast, silent, and humbling. And yet, despite this isolation, the vast number of stars, planets, and potentially habitable worlds suggests life might exist elsewhere, but the silence persists. Our signals have barely crossed a fraction of the Milky Way, fading as they go. Detecting or contacting another civilization is like shouting across the ocean, hoping the right ears will catch your voice amidst the infinite waves. In the end, understanding light years isn't just a measurement of distance, it's a window into time, isolation, possibility, and perspective. It shows us how tiny, fragile, and fleeting our existence is, yet also how connected we are to the vast cosmic story unfolding around us. Every photon of starlight entering your eyes tonight carries not just information, but a journey across space and time, bridging epochs, worlds, and unimaginable distances, reminding us of our place in the grand universe. You don't need to think about Proxima Centauri being 4.24 light-years away when deciding what to have for breakfast, whether to take an umbrella or which route to take to work. The day-to-day details of life happen entirely within your local world. Yet, there is value in occasionally stepping back, in pausing to contemplate the immense scales of space and time that surround us. Doing so can give perspective, a sense of humility, and even a strange kind of comfort. When you realize that Earth is a small planet orbiting an ordinary star, that the nearest star beyond our Sun is over 4 light-years away, and that our Milky Way contains hundreds of billions of stars, it can shift the way you see your own life. Beyond that, there are trillions of galaxies in the observable universe, each one filled with stars, planets, dust, and the slow evolution of cosmic history, stretching across billions of years. Your problems, whatever they may be, exist on a tiny speck in this immense expanse. The argument you had with a friend, the stress at work, the anxiety about the future, the heartbreak, the frustration, all of it unfolds on one small, fragile world. The nearest star does not care about your problems. The galaxy does not notice. The universe continues its silent, majestic evolution, completely indifferent to human affairs. And yet, that indifference can be strangely liberating. It reminds you that the things that feel overwhelming today are temporary and local. They exist in a world teeming with complexity and life, yet they are just one thread in the vast tapestry of space and time. This is not to diminish your experience. Pain, joy, love, fear, and hope are real. They matter deeply to you, and that is what gives them significance. But from a cosmic perspective, these moments are contained, finite, and part of something far larger. There is also something profoundly beautiful about understanding light years. When you look up at the night sky, you're not just seeing points of light twinkling at random. Each star is a messenger from the past, photons traveling for years, decades, or even centuries before reaching your eyes. In that moment, you are connected across vast distances of space and time, a tiny conscious observer of a universe in motion. You are made of the same material as those stars' atoms, forged in the cores of previous generations of stars, scattered across the cosmos, and recombined into planets, oceans, life, and consciousness. Every star has a story. Some are young, freshly ignited from collapsing clouds of gas and dust, beginning their lives as nuclear furnaces. Some are middle-aged, like our Sun, burning hydrogen steadily in their cores, stable and long-lived. Others are ancient, approaching the end of their lives, having exhausted their fuel. Some will fade into white dwarfs, slowly cooling over trillions of years. Others will explode as supernovae, scattering their atoms across space to be recycled into new stars, new planets, and perhaps the building blocks of life. And all of them are separated by distances so vast that light itself requires years, centuries, or millennia to travel between them. The universe is sparse, a cosmic archipelago of light, surrounded by enormous oceans of darkness. And yet, those islands are connected by light, by gravity, by the shared atoms that flow through stars, planets, and living beings. Every atom in your body was forged in the heart of a star long gone, scattered across space, and eventually gathered into the molecules that make you, the planet you stand on, and the life around you. In looking at the stars, you are witnessing the universe looking back, an intricate dance of matter and energy that stretches across time and space. As our technology improves, our ability to measure distances in light years becomes more precise, revealing the galaxy in greater detail than ever before. The Gaia spacecraft is mapping over 1 billion stars in 3 dimensions, creating the most precise map of our Milky Way to date. The James Webb Space Telescope is already detecting galaxies over 13 billion light-years away, glimpsing a universe that existed shortly after the Big Bang. And future observatories will push even farther, peering into the earliest moments of cosmic history. We are also discovering more and more exoplanets, thousands confirmed, and thousands more waiting to be verified. Some lie dozens, even hundreds of light years away, orbiting stars we can only just begin to study. These discoveries reveal the astonishing variety and abundance of worlds. Rocky planets like Earth, gas giants like Jupiter, icy bodies on the fringes of their systems. Planets are everywhere. Some may harbor life, simple or complex. Others may be barren, yet even their presence tells us something profound about the universe. That creation is relentless and prolific. That planets and stars are the norm, not the exception. Understanding light years, therefore, is not just a lesson in distance. It is a lesson in time, perspective, and connection. Every photon that reaches your eye carries a story of creation, survival, and change across incomprehensible distances. Every star you see is a living relic of a history far beyond human comprehension. And even if we never visit most of these worlds, even if we never send humans beyond our own solar system, they are there. They exist. They shine. They endure. And in witnessing them, you participate in the vast cosmic narrative of which you are a small yet essential part. In the future, we might send robotic probes to nearby stars. Ambitious projects like Breakthrough Starshot propose sending tiny, gram-scale spacecraft to Proxima Centauri, accelerated by powerful ground-based lasers. Even if such a mission succeeds, the probes would take over 4 years to send back the first data. And that is for our nearest stellar neighbor, our closest opportunity to extend humanity's reach beyond the sun. For stars farther away, the delays would stretch into decades, centuries, or millennia. Yet, even with the most revolutionary engineering, light years remain a fundamental barrier. The distances between stars are vast, and light speed is finite. This isn't a limitation to be overcome like climbing a mountain or building a taller rocket. It is a fundamental property of the universe, baked into the very fabric of space and time. It defines the structure of reality and the scale on which we can act. Light years are the unit by which the universe measures itself. They are the cosmic ruler, the pulse of distance and time combined. Understanding light years reshapes how we see our place in the universe. It changes the way we think about human endeavors, life, and the future of our species. These aren't abstract philosophical questions, they have real implications for the future of space exploration, the search for extraterrestrial life, and the long-term survival of humanity. They force us to confront our limitations and simultaneously inspire us to imagine new possibilities. For most of human history, the universe felt small. Ancient civilizations imagined the stars as lights attached to a celestial sphere just beyond the moon and planets. The cosmos was a finite dome you could, in theory, reach if you climbed high enough. Even after realizing the stars were distant suns, their true distances were inconceivable. A few million kilometers? A few billion? The numbers were abstract, beyond comprehension, almost poetic in their enormity. It wasn't until the early 20th century that we began to measure these distances accurately, and the true immensity of space revealed itself. In 1918, Harlow Shapley calculated the size of the Milky Way, showing it to be about 100,000 light-years across. Astronomers were stunned. The universe was far larger than anyone had imagined. Then, in 1929, Edwin Hubble demonstrated that spiral nebulae were not clouds within our galaxy, but entire galaxies millions of light-years away. The universe expanded again, not physically, but conceptually, dwarfing every previous notion of cosmic scale. Humanity went from believing the Milky Way was the entire universe to realizing it was just one galaxy among billions. Today, we know the observable universe stretches roughly 93 billion light-years across and contains an estimated 2 trillion galaxies. This number is almost incomprehensible. Every galaxy contains billions or even trillions of stars, most likely surrounded by planets, many potentially capable of harboring life. And yet, these numbers are not just abstractions. They describe a real physical space that surrounds us in every direction. If you could see far enough, you would witness galaxies receding into the distance, more and more of them, until finally reaching the cosmic horizon, the limit imposed not by the strength of your telescope, but by the finite age of the universe and the speed of light itself. Beyond that horizon, light simply hasn't had time to reach us, and we remain forever cut off from what lies beyond. This knowledge transforms our perspective in profound ways. We are not at the center of the universe. We are not special in any cosmic sense. Earth is a typical planet orbiting a typical star in a typical galaxy, located in a relatively average region of space. There is nothing unique about our position. If you were transported to another galaxy billions of light-years away, the view would feel familiar. Stars scattered across the darkness, galaxies spinning silently, each following the same cosmic laws. Yet, even amid this apparent ordinariness, there is a beauty that is uniquely ours to behold. The stars, though ordinary, are far away and ancient. The light reaching your eyes tonight left some of those stars centuries, millennia, or even billions of years ago. Every point of light is a messenger from the past, a thread connecting us to the deep history of the universe. The very atoms in our bodies were forged in ancient stars, long extinguished, scattered across the cosmos, and recombined into planets, oceans, life, and consciousness. To look at the night sky is to witness a grand cosmic story of creation, destruction, and rebirth. A story in which we are intimately involved, even if only for a fleeting moment. The distances we measure in light years are more than numbers. They are a reminder of time itself. They show us that every action, every thought, every discovery exists within a vast temporal context. The universe does not rush, nor does it wait. It unfolds at its own pace, indifferent yet magnificent. And in understanding this, we can appreciate both the fragility and the resilience of life. the fleeting nature of human existence, and the enduring grandeur of the cosmos. Galaxies stretch in every direction, fading into the cosmic horizon, a seemingly endless expanse of stars, dust, and light. From any vantage point, the universe looks remarkably similar, homogeneous on the largest scales, yet filled with intricate detail when we look closer. This duality is both humbling and empowering. It is humbling because it puts our lives into perspective. Every empire, every war, every triumph and failure in human history has occurred on one small planet in a minor spiral arm of one typical galaxy, billions of light years away from countless others. From the vantage point of the universe, our existence is fleeting, almost invisible, a brief flicker of awareness in a vast cosmic ocean. We are like microscopic organisms floating in a droplet of water, scarcely aware of the boundless universe surrounding us. The sheer scale is staggering. The light from galaxies, billions of light years away, began its journey long before our species existed, long before life as we know it began on Earth. Every photon that reaches us carries a story of the distant past, a whisper from a time when the universe was young, chaotic, and still forming its first stars and galaxies. Yet there is empowerment in this perspective as well. Despite our smallness, we are capable of understanding the universe at a scale that dwarfs us. We have built telescopes that can see galaxies billions of light years away, spacecraft that traverse the solar system, and mathematical models that describe the evolution of the cosmos. We are tiny, yet conscious and capable, able to comprehend the workings of a universe far larger than ourselves. That ability to observe, measure, and reason about something so vast is nothing short of extraordinary. Understanding light years and cosmic distances also forces us to confront difficult truths about space exploration and humanity's future. The distances are so enormous that they may represent fundamental barriers, obstacles that may never be fully overcome, no matter how advanced our technology becomes. Consider what it would take to send humans to another star. Proxima Centauri, our nearest stellar neighbor, is 4.24 light-years away. The fastest spacecraft humans have ever built, the Parker Solar Probe, reaches speeds of about 192 kilometers per second. At that rate, it would take roughly 6,800 years to arrive at Proxima Centauri. To put that into perspective, a journey launched when humans first invented writing would not even have reached the star yet. Even if we imagine revolutionary new propulsion systems capable of 10% of light speed, a velocity unimaginably faster than anything we can currently achieve, it would still take over 42 years to reach Proxima Centauri. A mission of that kind would outlast entire careers, span multiple generations, and require meticulous planning for every foreseeable contingency. And that is just for the closest star. Most stars are many light years farther, with travel times stretching into centuries or millennia, even with the most advanced theoretical propulsion. The engineering challenges are enormous. Accelerating a spacecraft to even a fraction of light speed requires staggering amounts of energy. Protecting a human crew from cosmic radiation over decades of exposure presents monumental biological and technological problems. Life support systems must function flawlessly for decades without resupply. Psychological challenges are profound. Imagine living your entire life in a confined metal tube, watching only the stars, knowing that you will likely never see Earth again. The vast emptiness of interstellar space is isolating. There are no landmarks, no familiar sights, nothing but darkness stretching in every direction. Even a brief failure in life support or navigation could be catastrophic, with no rescue possible. Interstellar travel forces us to confront time in a new way. At near-light speeds, the familiar rhythm of life is disrupted. Time dilation, as predicted by Einstein, means that while decades might pass on Earth, travelers may experience only a fraction of that time. Imagine leaving Earth in your 20s and returning centuries later to find that everyone you knew, every trace of your familiar world, is long gone. Humanity itself would have evolved in your absence, and you would arrive in a future that is essentially alien. Yet, despite these immense challenges, the idea of traveling to the stars continues to inspire. It stretches our imagination and pushes the boundaries of human ingenuity. It forces us to think about the future in multi-generational terms, about building civilizations and technologies that may outlast our own lifetimes. Even if the first interstellar missions are robotic, their successes or failures will define how humanity approaches the stars for centuries to come. In the end, the enormity of interstellar distances is both a barrier and a beacon. It reminds us of our fragility and the limits of our reach, but it also underscores the magnitude of our potential. To understand light years is to understand both our smallness and our greatness. We are tiny observers on a pale blue dot, yet capable of glimpsing the cosmic tapestry that surrounds us, capable of planning, imagining, and even one day reaching beyond the confines of our solar system. Even if we detected their signals, the delay imposed by light years becomes immediately apparent. A civilization 50 light years away is 50 years in our past. The signals we receive today left their planet half a century ago. If we immediately respond with our own radio message, it would take another 50 years to reach them. That's a 100-year round trip for a single exchange of information. You could ask a question about their technology, society, or scientific discoveries and die long before receiving an answer. Even if your descendants survive to get a reply, the world they live in might be unrecognizable compared to the one you knew. Now imagine civilizations hundreds or thousands of light years apart. Exchanges would span millennia, with each message traveling through time as well as space. By the time a reply arrives, both civilizations may have evolved, migrated, or even gone extinct. Communication across interstellar distances becomes a game of patience beyond human comprehension. This is one of the key reasons the Fermi paradox remains so puzzling. Intelligent life might exist everywhere, yet the sheer vastness of space and time, measured in light years, creates practical isolation, even for technologically advanced species. It's not just the delay that matters. Signals weaken with distance, spreading out into an ever-expanding sphere. By the time a radio transmission from 50 light-years away reaches us, the energy is minuscule. Detecting it requires extremely sensitive instruments aimed precisely at the source. Even then, interference from cosmic background radiation, interstellar dust, and natural astronomical sources can easily mask or distort the signal. The odds of perfect alignment, frequency, timing, and pointing are astronomically small, The universe may be teeming with civilizations, yet our ability to perceive or communicate with them is crippled by distance. For practical purposes, light years define a limit to interstellar interaction. Even if humans or aliens could survive for thousands of years, the delays imposed by light-speed communication make meaningful dialogue almost impossible. Civilizations separated by more than a few dozen light-years may as well be isolated islands in a cosmic ocean, unable to influence one another in real time. Every attempt to send a message is an investment across generations, not years or decades. It's a humbling reminder of how vast and disconnected the universe truly is, despite the shared physics and chemistry that bind all matter. And yet, there's a certain beauty in that isolation. Each star system, each civilization, whether aware of others or not, is a self-contained story unfolding in its own corner of the cosmos. The light that travels to us carries the memory of those distant places, their history preserved in photons that journey for decades, centuries, or millennia. When we detect a signal, we are literally hearing a message from the past, a connection not across space alone, but across time itself. In this sense, light years are more than a measure of distance. They are a measure of time, a cosmic ledger linking the present to the distant past. They remind us of the limitations imposed by the universe, but also of the potential for connection across unimaginable scales. Every probe we send, every signal we broadcast, and every observation we make is a gesture across the void, reaching out to the stars with patience that exceeds our human lifetimes. The vast distances of light years challenge our imagination, ambition, and patience. They force us to think in terms of generations, not years, of civilizations, not individuals, of cosmic epochs, not single human lifespans. They define the rules for everything we attempt in space, from exploration to communication to the very possibility of encountering alien life. And in that, they give us perspective. While our daily concerns seem immediate and urgent, the universe moves at a scale that dwarfs all human endeavor. Yet we are here, observing, learning, and reaching out, proving that even in a cosmos measured in light years, life can make itself known. When we think in terms of light years, we are forced to confront the vastness of the universe in a way that is almost incomprehensible. A single light year, the distance light travels in one Earth year, is nearly 10 trillion kilometers. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away, which means that even if we sent a signal traveling at the speed of light, it would take over 4 years to reach it. Any reply would take another 4 years. That is the reality of cosmic distances. Everything is separated not just by space, but by time itself. This separation transforms our thinking about civilization, communication, and connection. Even if advanced technological civilizations exist elsewhere in the galaxy, the sheer distances ensure that contact, in any meaningful, real-time sense, is almost certainly impossible. The stars we see at night may already be gone, their light only now arriving at Earth. The galaxies we observe billions of light-years away show us the universe as it was billions of years ago. We are constantly looking into the past, connected to cosmic events that happened long before humans even existed. The implications for potential contact with alien civilizations are staggering. Imagine a civilization 50 light-years away, broadcasting its knowledge, its culture, its discoveries into space. Their signals, traveling at light speed, will reach us only decades after they were sent. If we respond immediately, it will take another 50 years for our message to reach them. A single exchange, a single conversation spans a century. For civilizations separated by thousands of light years, meaningful dialogue is literally impossible. Any interaction would be asynchronous, archival, and delayed. Civilizations might rise, flourish, and disappear without ever intersecting. Messages could arrive from civilizations that no longer exist, leaving us in contact with ghosts of the past. This is why the Fermi paradox, the question of why we haven't seen evidence of extraterrestrial intelligence, is so haunting. The universe may be teeming with life, yet the distances are so immense that each civilization is effectively isolated, unable to know about the others. Even if every star had an intelligent civilization, the light years between them act as invisible barriers, preventing real contact. Civilizations may exist in solitude, rising and falling in their own pockets of the galaxy, unaware of the existence of others. Each life form, each society, is alone in its own time and space, learning, exploring, and eventually fading into history. Even closer to home, the implications of light years affect our thinking about interstellar travel. With current technology, sending humans to another star is effectively impossible. The fastest spacecraft we've built would take thousands of years to reach even Proxima Centauri. To survive, travelers would need multi-generational ships, small moving civilizations aboard vessels isolated from Earth for centuries. They would evolve their own cultures, laws, and identities, completely cut off from the world they left behind. Or we might dream of cryogenic sleep, suspending humans for the journey. Yet the technology remains science fiction, and the challenges biological, psychological, and societal are immense. The speed of light is a hard limit, a cosmic boundary we cannot overcome. But while the universe imposes these limits, it also offers a perspective that is both humbling and empowering. Humbling because, when measured against cosmic time and distance, human struggles, conflicts, and ambitions are infinitesimal. Wars, politics, and personal dramas occur on a tiny planet, orbiting a typical star in an unremarkable galaxy, a speck of dust in a vast cosmic ocean. The stars, the galaxies, and the void between them continue on their slow, majestic evolution, indifferent to our lives, our triumphs, and our tragedies. And yet, it is empowering because we can comprehend this universe. We are capable of measuring distances in light years, mapping billions of stars, sending probes to the edges of the solar system, and understanding the laws that govern galaxies billions of light years away. In the midst of a universe so vast, conscious beings have arisen, capable of reflection, curiosity, and knowledge. We may be physically small, but intellectually and creatively, we are enormous. Light years also teach us a profound lesson about time. The photons that reach our eyes tonight may have traveled for thousands, millions, or even billions of years, originating in stars long dead. Every time we look up at the night sky, we are looking into the past. We are participating in a dialogue with history itself. connected to events and worlds that no longer exist. There is a strange comfort in this. It reminds us of the continuity of the cosmos, that life, matter, and energy persist far beyond individual human lifetimes. Understanding the scale of light years also reframes our place in the universe. While we may be isolated, we are not insignificant in our capacity to explore, to understand, and to imagine. The isolation imposed by the light-year scale challenges us to think differently about society, governance, communication, and cooperation. If humanity ever reaches for the stars, we will need to adapt to delayed communication, autonomous colonies, and the reality that civilization may evolve differently on each world. The universe requires patience, foresight, and a willingness to accept that some goals, like real-time interstellar dialogue, are impossible. And yet, in this immensity, there is beauty. Every star is a story, every galaxy a history, every photon a connection across time and space. The atoms in our bodies were forged in ancient stars, scattered and recycled into new generations of worlds until they became us. When we understand light years, we understand not only distance, but also the threads of connection that weave through the cosmos, linking us to everything that came before and everything that will ever come after. In the end, light years are more than a measure of distance. They are a measure of perspective, of humility, of potential, and of connection. They remind us that the universe is vast. Life may be rare and isolated, and yet we are part of it. We are observers, participants, and descendants of a story that spans billions of years and unimaginable distances. Every glance at the night sky is an invitation to reflect on our place in this cosmic tapestry, to dream boldly, and to marvel at the vastness in which we live. There's something profoundly melancholic about realizing the scale of the universe. Humans are inherently social creatures. Connection, community, communication, these are fundamental to who we are. We thrive on shared experience, on the exchange of ideas, on empathy and understanding. And yet, when we look out into the universe, we see vast distances that make connection nearly impossible. A star a few dozen light years away might host a civilization as advanced as ours. Yet even if they're broadcasting signals, we could never carry on a meaningful conversation. By the time we receive a reply, decades or centuries might have passed. Entire generations would have lived and died in the meantime. Isolation becomes a cosmic inevitability. Even within our own galaxy, the nearest civilizations, if they exist, are separated by thousands of light years. Across these distances, communication is more like archaeology than conversation. Every message is delayed by the tyranny of light speed, every interaction stretching across decades or millennia. And yet, there's a strange beauty in this isolation. It means that every civilization that does arise is precious. Every conscious mind is a unique spark in a vast cosmic ocean. Every act of creation, every moment of love, every discovery, every question asked of the universe is unique and irreplaceable. We might be alone, or effectively alone, in our region of space, and that alone makes what we do matter more, not less. Our art, our science, our stories, our lives, they are cosmic acts of significance, precisely because they might not exist anywhere else nearby. When we gaze at the night sky, we are not just looking at points of light. We are witnessing messages from the past, photons that have traveled for years, centuries, or millennia, connecting us to moments long gone. We are seeing stars as they were, not as they are. And in doing so, we are participating in a dialogue across time itself. Consider Sirius, the brightest star in our night sky, 8.6 light-years away. Its light began its journey before many of us were born. Yet tonight, it reaches our eyes. Or Betelgeuse, the massive red supergiant in Orion, 550 light-years away. Its light began its journey during the Renaissance. When we see it, we are seeing a star frozen in time as humans painted, built cathedrals, and explored new continents. Every night, the sky is a museum of cosmic history, a gallery of distant lights illuminating the past. A light year is more than a measure of distance. It is a measure of time and perspective. It reminds us that distance and time are intertwined in the fabric of space-time itself. Traveling even a fraction of the speed of light across these vast distances is a challenge that defies imagination. A journey to the nearest star using our fastest spacecraft would take thousands of years, longer than recorded human history. The Milky Way, a galaxy of 100,000 light-years across, is so immense that even light would require 100 millennia to cross it. And the observable universe, spanning 93 billion light-years and containing an estimated 2 trillion galaxies, is so large that our human minds struggle to grasp it. And yet, understanding this scale does more than humble us. It empowers us. It shows us the extraordinary nature of consciousness itself. For all our smallness, we have the capacity to measure the stars, map the galaxy, and understand the laws of physics that govern the cosmos. We can send probes to the edge of the solar system, observe galaxies billions of light-years away, and even imagine civilizations on planets orbiting distant suns. The light year is a reminder that while we may be small in scale, our curiosity, creativity, and understanding are vast. Every star is a story. Some are young, just forming from clouds of gas and dust. Some are middle-aged, stable like our Sunday. Some are old, dying, scattering their elements into space to seed new generations of stars and planets. Every star we see is part of a grand cosmic cycle of creation, destruction, and rebirth. And through the light they emit, they communicate across time, offering us glimpses of their life histories. In contemplating light years, we confront profound truths about our place in the universe. We are small. We are isolated. Our connection to others may be constrained by physical laws. Yet in that isolation, there is meaning. Every choice we make, every thought we have, every connection we forge here on Earth becomes all the more precious. We are the universe aware of itself in this corner of space. Our lives, though brief in cosmic time, are acts of wonder, discovery, and consciousness. So when you look up at the stars tonight, remember, each one is a beacon from the past, a story traveling across light years to reach you. Every flicker of light reminds you of the immense scale of space and the fleeting nature of human life. And yet, paradoxically, it also reminds you of the unique power we hold as conscious beings to understand, to marvel, and to create. Light years are not just distances, they are time machines, threads of connection, and instruments of perspective. They teach us humility and wonder, isolation and significance, the impermanence of life and the permanence of the cosmos. And in that understanding, we find both melancholy and beauty. We figured this out. We measured distances across incomprehensible expanses. We devised ways to see stars billions of light years away. We sent spacecraft that have now passed the boundaries of our solar system, carrying messages and human curiosity into the void. We have built telescopes that capture photons that began their journey long before human civilization existed. And in doing so, we have learned that the universe is far vaster, far older, and far stranger than our ancestors ever imagined. The speed of light is not just a number. It is a fundamental property of reality, woven into the very fabric of space and time. It sets the ultimate speed limit for everything with mass, and even information itself cannot outrun it. This is not a technological problem, something we might overcome with better engines or exotic propulsion systems. This is how the universe works. Light years are more than units of measurement. They are a reminder that distance and time are inseparable in the cosmos. To reach the nearest star, even traveling at an impossible speed, would take years. To traverse our galaxy, millennia. To cross the observable universe, billions of years. And yet, despite these barriers, we have learned to reach across space with our minds and with our technology. We have mapped billions of stars, charting their locations and movements. We have discovered thousands of exoplanets, some potentially capable of harboring life. We have observed the faint glow of galaxies billions of light years away, seeing them as they were when the universe was young, in its infancy shortly after the Big Bang. Every photon that reaches us is a message from the past, a story traveling across time and space to arrive in this very moment. The universe is expanding. Space itself stretches, carrying galaxies away from one another, driven by a mysterious dark energy whose nature remains one of the greatest puzzles of modern physics. Far distant galaxies are receding from us faster than their light can reach us. In the future, the cosmos will appear even emptier from our perspective, as more and more galaxies slip beyond our cosmic horizon, forever unreachable. The isolation imposed by the light year is profound, and yet it has not stopped us from understanding the universe. Even as the cosmos stretches beyond our reach, we have found ways to see it. Telescopes such as the Hubble and James Webb Space Telescope peer billions of light years into the past, revealing galaxies forming when the universe was just a fraction of its current age. The light from those galaxies has traveled longer than all recorded human history, carrying information that allows us to reconstruct the universe's earliest moments. The light year is our lens into time itself, connecting us to events that happened before humans even walked the earth. When you look up at the night sky tonight, consider this. The photons striking your eyes may have been traveling for hundreds, thousands, or millions of years. You are seeing the universe not as it is, but as it was. Every star is a time machine. Every galaxy is a record of history written in light. And yet, all of this vastness exists around us, here on our tiny planet, orbiting an ordinary star in a galaxy among trillions. We are small, yes. Isolated, yes. but we are also the ones who see, who understand, who measure, who wonder. There is humility in this knowledge. Our lives are brief. Our problems are temporary. The petty struggles and fleeting triumphs of daily existence are local, ephemeral. From a cosmic perspective, they are almost invisible. And yet, there is beauty and empowerment in this realization. Because we exist in a universe so vast, so incomprehensible, yet we can comprehend it at all. We are the consciousness of the cosmos looking back at itself. The universe may be indifferent, but we are aware. The universe may be ancient, but we are alive. And in that awareness, in that capacity to measure, to understand, to imagine, lies a profound significance. We have built tools that allow us to measure light years, parse cosmic history, and map the unseen. We have sent messages across the solar system and glimpsed the universe beyond. Our knowledge of the cosmos grows daily, slowly illuminating the scale, the beauty, and the loneliness of space. And in this knowledge, we find perspective. Our lives, though short, are meaningful precisely because they are finite. Our existence, though small, is remarkable because it is conscious. A light year is more than 9.46 trillion kilometers. It is a bridge between time and space, between isolation and connection, between the ephemeral and the eternal. It reminds us of the immense scale of the universe, the limits imposed by the laws of physics, and the incredible achievements of human curiosity. It humbles us, it challenges us, and yet it empowers us. It tells us, though we are small, we are capable of understanding the cosmos. Though we are fleeting, our consciousness is vast. Though we are alone, our awareness transforms isolation into significance. And perhaps, in contemplating light years, in contemplating the vast emptiness that separates the stars, we find our place not at the center of the universe, but as its observers, explorers, and storytellers. In a cosmos of unimaginable scale, we are the minds that ask questions, the eyes that seek light, the beings who dare to understand. And that, ultimately, is something extraordinary. Despite being small creatures on a small planet, we have measured these vast distances. We have peered across the darkness and learned to comprehend scales that dwarf human imagination. We understood our place in the universe. We built telescopes and spacecraft and developed mathematical frameworks that allowed us to see galaxies billions of light years away, cosmic structures formed when the universe itself was in its infancy. We are tiny, confined to one small world for now, yet we are also remarkably capable. We are conscious beings who can grasp the universe that created us, who can look up at the night sky and understand, at least conceptually, the incredible scales of space and time. We can contemplate distances measured in trillions of kilometers, time spans measured in billions of years, and a cosmos that stretches far beyond what our eyes can see. From a cosmic perspective, you are insignificant. Your life is a fleeting flicker, perhaps lasting 80 or 90 years if fortune favors you, in a universe that has endured for 8 billion years, and will continue, in some form, for trillions more. You exist for the blink of an eye, on a tiny planet orbiting an ordinary star, a speck of matter drifting through the vast darkness. And yet, you are also extraordinary. You are made of atoms, forged in the hearts of stars that lived and died billions of years ago. Their matter scattered across space, coalesced into new stars and planets, and eventually became you. You are literally made of stardust, the product of processes that have been unfolding for eons. You are the universe made conscious, a way for the cosmos to know itself, to appreciate its own grandeur and complexity. So, the next time you gaze up at the stars on a clear night, consider what you are really seeing. Those points of light scattered across the blackness are not just specks, they are distant suns. Massive balls of fusing hydrogen, each potentially hosting its own family of planets and moons. They are light years away, separated from us by distances so immense that the photons entering your eyes have traveled for years, decades, even centuries. Some of that light began its journey before you were born, some before your grandparents were born, carrying the story of a star across space and time to reach you. In that sense, you are intimately connected to those distant suns, linked by light that has traversed the cosmic void. You are looking into the past, into the history of the universe itself, and that history has now reached you. The universe is immense beyond comprehension. You are small, a single person on a single planet, and yet your consciousness allows you to perceive it, to understand it, and to feel its weight. You can grasp the vast distances, the billions of stars, the trillions of planets, and the incredible span of time over which cosmic processes unfold. This understanding is rare. It is precious. It is the hallmark of our species. We alone have the capacity to comprehend infinity while simultaneously experiencing our own smallness. We can feel humbled by the enormity of the cosmos and empowered by the fact that we can measure, understand, and even participate in it through observation and imagination. And perhaps this is the most important lesson to take away from understanding light years. It is not only about the technical definition, a distance of 9.46 trillion kilometers, the distance light travels in 1 year. It is about perspective. It is about what it means for us as humans, for our place in the universe, for our future. We live at a unique moment in history. We are the first generation to truly comprehend the scale of the cosmos, to measure the distances to the stars, to detect planets orbiting suns far beyond our own, to trace the light of galaxies from when the universe was young. Our ancestors looked up at the same stars, wondered about the same mysteries, but they lacked the knowledge, the tools, and the means to measure them. They could not know that the stars were distant suns, that the Milky Way was one galaxy among billions, that the light from some galaxies began its journey before Earth itself formed. In understanding light years, we touch something profound. We feel the tension between our insignificance and our capacity for greatness. We see the loneliness of life in the vast cosmos, but also the rare privilege of being conscious, of being able to explore, to question, to seek meaning. Light years are both a barrier and a bridge. They separate us from distant worlds, but they also connect us to the universe through the light that reaches us, carrying stories from across space and time. To comprehend a light year is to comprehend that the universe is not just out there. It is also in here, within us, in our ability to think, to wonder, and to understand. We are small, yet conscious, brief, yet capable of grasping eternity, alone, yet connected to the cosmos in ways that our ancestors could never have imagined. And in that knowledge, there is both humility and power. We are the universe looking at itself, asking questions, seeking understanding, and marveling at the vast, beautiful, indifferent expanse that surrounds us. They couldn't know that those suns were light years away. They couldn't comprehend the vast distances that separate us from the rest of the universe. But we can. We can measure, calculate, and understand these distances with precision. We know that Proxima Centauri, our nearest stellar neighbor, is 4.24 light-years away. We know that the Andromeda Galaxy, our closest galactic companion, is 2.5 million light-years distant. We know that the observable universe stretches nearly 93 billion light-years across space. These aren't vague guesses or rough estimates. They are measurements, confirmed and refined over decades of careful observation, using telescopes, satellites, and mathematical models that allow us to map the universe in ever greater detail. This knowledge changes us. It must. When you truly grasp that the nearest star would take thousands of years to reach with our current technology, that the light from distant galaxies has been traveling for billions of years to reach your eyes, that the universe is filled with distances so vast that even radio signals take decades to traverse them, your perspective shifts. You begin to see the world differently. You realize that the things we fight over, arguments, borders, petty conflicts, are insignificant on a cosmic scale. All of it happens on a single, fragile planet in a vast and largely indifferent universe. We are together on this small world, orbiting an ordinary star, separated from our nearest stellar neighbors by distances measured in light years. From that vantage point, the divisions between us fade. What matters is what we share: life, curiosity, consciousness, the ability to ask questions and seek understanding. It also makes our existence feel more precious. If we are alone, or effectively alone, because the distances separating us from any other potential intelligence are so vast, then everything we do here matters tremendously. We might be the only minds in our cosmic neighborhood capable of contemplating the universe, capable of creating art, discovering scientific truths, feeling love, compassion, and wonder. That responsibility is staggering. It means we must care for our planet, this tiny island of life, drifting in a cosmic ocean. It means we must preserve the knowledge we have gained, protect the understanding we have developed, and think in terms far beyond the fleeting concerns of our lifetimes. We must consider not only the next year or decade, but the next century, the next millennium, and the long future of humanity among the stars. The light year is more than just a unit of measurement. It is a symbol, a bridge, a reminder of our place in the universe. It reminds us that we are part of something unimaginably vast, yet that within this vastness, we are unique and precious. It reminds us that the stars are both incredibly distant and intimately connected to us through the light that has traveled across space for years, decades, centuries, and even millennia to reach us. Every time you look up at the night sky, you are participating in something ancient and profound. You are seeing across light years, into the past, into the history of the cosmos itself. You are witnessing the universe in all its beauty, complexity, and wonder, and you are part of it, made of the same atoms forged in stars billions of years ago, governed by the same physical laws, bound by the same fundamental forces that shape everything from the tiniest particle to the largest galaxy cluster. That is what a light year truly represents, not merely distance, but connection, not merely isolation, but belonging, not only our smallness, but our significance within that smallness. You are part of this cosmos, and the universe is, in a very real sense, experiencing itself through you. To understand light years is to understand both your insignificance and your extraordinary capacity to comprehend and appreciate the universe. Thank you for joining me on this journey through space and time. If this exploration has moved you, if it has opened your mind to the vastness surrounding us, a like or a subscription helps support more journeys like this. Remember, every time you look up at the night sky, you are seeing across light years. You are seeing the universe. And the universe, as vast and mysterious as it is yours to explore. Good night, and may you never look at the stars in the same way again.